A black dwarf, in case you haven't encountered the term before, is what happens at the very end of a certain kind of star's life. Stars like our Sun, medium-sized, steady, unassuming, don't go out in explosions when they die. They don't collapse into black holes or neutron stars, those exotic, violent endpoints reserved for much larger suns. Instead, they slowly, quietly become what is known as a white dwarf. A white dwarf is essentially the leftover core of a dead star. Very small, very dense, very hot, but no longer burning, no longer fusing. Just cooling. Radiating away the heat it accumulated over billions of years of fusion. Like a stone that was warmed by a fire slowly releasing that warmth into a cold room, long after the fire has gone out. A white dwarf cooling. That's the process. And it is an extraordinarily slow process. So slow, in fact, that in the current age of the universe, which is already about 13.8 billion years old, an age that staggers the imagination all by itself, not a single white dwarf has had enough time to cool completely. Not one. Every white dwarf that has ever formed is still warm, still faintly glowing, still releasing the echoes of its former fire into the darkness around it. But given enough time, given truly, almost insanely enormous amounts of time, even a white dwarf will cool to the point where it no longer gives off any light at all, any heat at all. It becomes, in every meaningful sense, invisible. A cold, dark, inert sphere roughly the size of a planet, but with the mass of a star, drifting silently through a universe that has forgotten what light looks like. That is a black dwarf. And the era that bears their name is a time when the universe is full of them. Countless billions of these dark, silent remnants, spread across a cosmos that has grown so cold and so empty and so still that nothing much is happening anywhere. Not in any rush, anyway. Things are still occurring. We'll talk about what things. But they are occurring on timescales so enormous that the entire current age of the universe would seem like the blink of an eye by comparison. So that is where we are headed tonight. Not anywhere frightening. Not anywhere cold in the way that feels threatening. Just quiet. Just still. Just out into the deep, slow, dark future of everything. To a place where the universe has grown very old and very peaceful. And where the last stories of the cosmos are playing out in slow motion, patient and unhurried, in the dark. Think of this as a kind of journey. A journey outward through time, rather than through space. We'll move slowly. There is no need to rush. There is nowhere to rush to, not in the Black Dwarf Era. Slowness is, in fact, rather the point. And as we travel, I'll be here with you, explaining as we go, wandering alongside you, pausing when something deserves a pause. Because the universe, even at the very end of its story, is still full of things worth wondering about. Let's begin. Here is something remarkable. Something that, when you first hear it, might make you pause and tilt your head slightly, the way you do when a sentence doesn't quite land the way you expected it to. After everything we just explored, after all that talk of a cold, dark, starless universe, of silent remnants drifting through an endless night, of an era so distant and so still that even the concept of time seems to slow down around it. Here is the truth that sits quietly underneath all of it. Not a single black dwarf exists yet. Not one. In the entirety of this vast, ancient, 13.8 billion-year-old universe, with its hundreds of billions of galaxies, each containing hundreds of billions of stars, stars that have been living and dying and burning and fading since almost the very beginning of everything. Not a single star has yet had enough time to complete the full journey from bright, burning sun to cold, dark, invisible black dwarf. The universe, for all its age, is still too young. That is the twist. And I find it genuinely beautiful, in a quiet sort of way. Because it means that the era we are journeying toward tonight is not some relic of the past, not some ancient chapter that played out long before we arrived on the scene. It is something that hasn't happened yet. Something that is waiting, patiently, unimaginably far ahead of us in time. The Black Dwarf Era is the future, the deep, deep, almost incomprehensibly remote future. And in a sense, that makes it feel less like history and more like a destination. A destination we will never reach, of course, but one we can visit, in the quiet hours of the night, through the patient language of physics and imagination. Let's think about that number for a moment. 13.8 billion years. It is already, on its own, a number that the human mind cannot truly hold. We are not built for it. Our brains evolved to track the passage of seasons, the span of a human life, the rise and fall of civilizations. 1,000 years already feels abstract to us. 10,000 years, the entire span of recorded human history, is a stretch. 1,000,000 years is nearly impossible to feel in any real sense. 1 billion years is 1,000,000 millions, and the universe is nearly 14 of those. To try and make that even slightly tangible, if you compress the entire history of the universe into a single calendar year, with the Big Bang happening on the first second of the 1st of January, then our entire solar system wouldn't form until early September. Life on Earth wouldn't appear until late September. The dinosaurs would come and go in the last days of December. And the entirety of human civilization, every empire, every invention, every book ever written, every song ever sung, would occupy roughly the last 15 seconds of the 31st of December. We are newcomers, absolute newcomers, and yet we have the remarkable ability to sit here, in the final moments of that cosmic year, and think about what happens in the year after next, and the one after that, and the one 1,000,000,000,000 years from now. That is an astonishing thing about being human. We are brief, and we know it, and somehow that knowledge only makes us more curious about the parts of the story we'll never see. So the universe is 13.8 billion years old, and that sounds ancient. And it is ancient, by any measure that matters to us. But in the context of what we're talking about tonight, 13.8 billion years is practically the beginning. It is the first chapter of a book with more chapters than there are atoms in the observable universe. The stars that are alive today, including our own sun, sitting faithfully at the center of our solar system, burning its hydrogen, warming its planets, are early stars. Young stars in the grander scheme. The universe is still very much in what cosmologists sometimes call the Stelliferous Era. That word, stelliferous, simply means star-bearing or star-filled. And that is exactly what this period of the universe's history is, filled with stars. Luminous, active, churning with energy and light. We live in the bright time. The warm time. The time when the universe is, in a sense, most alive, most active, most energetic, most interesting in the ways that life tends to find interesting. And it is easy, living in this time, to assume that this is simply how things are. That stars are a permanent feature of reality, like gravity, or space itself. That they have always been here, and will always be here. But they won't. The Stelliferous Era, this great, glorious, star-filled age, will eventually come to an end. The gas clouds that give birth to new stars will thin out and disperse. The raw material of star-making will be used up. New stars will stop forming. And the ones that already exist will continue on their slow, inevitable journeys toward darkness. It will take an extraordinarily long time. The Stelliferous Era is expected to last for something in the range of 100 trillion years. A number so far beyond 13.8 billion that our current age becomes almost a rounding error. A footnote. A brief, bright flicker at the very start of the story. But 100 trillion years from now, give or take, the last star will burn out. And then the slow road to the Black Dwarf Era truly begins. Now, to understand what a black dwarf actually is, and why it takes so impossibly long to form, we need to take a gentle step back and talk about what happens to a star like our Sun when it reaches the end of its life. Because stars don't simply switch off. They don't burn brightly one day and go dark the next, like a light bulb blowing a fuse. The process is far slower, far more gradual, and in its own way, far more interesting than that. It begins, as most things in a star's life do, with hydrogen. Hydrogen is the simplest element in existence. A single proton, orbited by a single electron. It is also the most abundant element in the universe by a very wide margin. Roughly 3/4 of all ordinary matter in the cosmos is hydrogen. It was forged in the first few minutes after the Big Bang, when the universe was still extraordinarily hot and dense, and it has been the fundamental fuel of stars ever since. Deep inside a star, in the core, where the pressure and temperature reach almost unimaginable extremes, hydrogen atoms are squeezed together so forcefully that they fuse. Two hydrogen atoms become one helium atom, and in that transformation, a tiny but real quantity of matter is converted directly into energy. Light, heat, the warmth on your face on a sunny day, the photosynthesis happening in every green leaf. All of it tracing back, ultimately, to hydrogen fusing into helium in the heart of a star. This process, nuclear fusion, is what holds a star together. Because a star is, in a very fundamental sense, a balancing act. Gravity is constantly pulling all of that stellar material inward, trying to collapse the star into a single point. And the energy released by fusion is constantly pushing outward, resisting that collapse. For billions of years, these two forces hold each other in perfect equilibrium. The star neither collapses nor explodes. It simply burns. Steadily, faithfully, for a span of time that dwarfs the entire history of life on Earth many times over. But the hydrogen does not last forever. Gradually, over billions of years, the hydrogen in the core is consumed, converted to helium. And as it runs low, the balance begins to shift. The outward pressure of fusion weakens. Gravity gains the upper hand, just slightly, and begins to compress the core further. This compression, in turn, generates more heat, which causes the outer layers of the star to expand enormously, swelling outward into what is known as a red giant. Our own sun will do this one day, expanding far enough to engulf the inner planets, including, most likely, the Earth. It is a dramatic chapter, but not our chapter tonight. Tonight we're interested in what comes after the drama. After the red giant phase, a star like our sun, a medium-sized star, not too big, not too small, does something rather elegant. It gently sheds its outer layers. These layers drift away into space, expanding outward in a beautiful shell of glowing gas called a planetary nebula, one of the most visually stunning objects in the entire cosmos, glowing in rings of blue and red and gold as the hot core illuminates the departing gas from within. And what is left behind, once those outer layers have drifted away? A white dwarf, the core of the star, compressed now to roughly the size of the Earth, but still containing roughly the mass of the original sun. Extraordinarily dense, a teaspoon of white dwarf material would weigh about 5 tons here on Earth. No longer fusing, no longer burning, just hot. Enormously hot at first, glowing white, then fading slowly to yellow, then orange, then red, then eventually, given enough time, cooling to a deep, invisible black. That cooling process is what takes so long. Longer than the current age of the universe. Longer than the entire Stelliferous Era that lies ahead of us. The timescales involved are so large that physicists express them in powers of 10 rather than in years, because writing out all the zeros would serve no practical purpose. The shortest estimates for how long it takes a white dwarf to cool completely into a black dwarf are somewhere in the range of 1 followed by 15 zeros years. A quadrillion years. Others suggest it may take considerably longer, depending on the mass of the dwarf and the conditions around it. In any case, it hasn't happened yet. Not once. Not anywhere in the universe. Every white dwarf that exists right now is still warm. Still, in some tiny, fading way luminous. Still on that long, slow, patient journey toward complete darkness. And so the Black Dwarf Era waits. Somewhere impossibly far ahead in time. Patient as only the universe itself can be patient. Waiting for the cooling to finish. Waiting for the last ember to go cold. There is something I find almost meditative about this. The idea that the universe is not static. That it is always moving somewhere, always in the process of becoming something. And yet that the timescales involved in that becoming are so enormous that from where we sit, everything appears fixed. The stars look permanent. The galaxies look eternal. The universe looks like it has always been this way, and always will be. But it hasn't. And it won't. It is changing. Right now, tonight, as you listen to this. White dwarfs that formed billions of years ago are a tiny, imperceptible fraction of a degree cooler than they were yesterday. The universe is aging. The Stelliferous Era is ticking forward, slowly but certainly, toward its eventual close. And somewhere, in the unimaginably far future, when the last star has finally gone out and the last white dwarf has finally cooled, the Black Dwarf Era will begin. Not with a bang. Not with any drama at all. Just with a quiet, final settling into darkness. And then, in that darkness, something extraordinary will still be happening. Slowly, patiently, on timescales that make the current age of the universe look like the briefest of moments. But we'll get to that. For now, just rest in this thought, that the universe is older than almost anything we can imagine, and yet the story is still, in so many ways, only just beginning. Close your eyes if you like. Let the darkness be comfortable. Let it be vast and still and patient. There is no hurry. There never is out here. The Black Dwarf Era, Segment 3, The Life After Death of Stars. Death, in the universe, is rarely a sudden thing. It doesn't tend to arrive all at once, in a single decisive moment, the way we sometimes imagine it might. Out here, in the vast slow machinery of the cosmos, endings are more like long, gradual exhales. A releasing, a settling, a quiet transformation from one state of being into another, stretched across timescales so immense that the word ending almost stops meaning what we think it means. Stars know this better than anything. A star spends its whole life, billions upon billions of years, in a kind of magnificent tension. Gravity pulling inward, fusion pushing outward. These two enormous forces locked in a balance so precise, so perfectly maintained, that the star barely changes at all from 1,000,000 years to the next. It simply burns. Steadily, reliably, with a patience that puts everything else in nature to shame. And then slowly, the fuel begins to run low. And the tension begins to shift. And what happens next is not really death, in the way we tend to picture death. It is more like a metamorphosis. A transformation into something entirely new. Something quieter, something denser. Something that will outlast the star's own burning lifetime by an almost incomprehensible margin. Tonight, we're going to spend some time with that something. We're going to sit with white dwarfs. To understand what a white dwarf is, it helps to first spend a little time with the star it came from. And since the most familiar star any of us has ever encountered is our own sun, let's start there. Our sun is, by stellar standards, fairly average. It is not especially large, not especially small, not especially hot or cold or bright or dim. It sits comfortably in the middle of the range of things a star can be, a category astronomers rather charmingly refer to as a main sequence star. A steady, ordinary, reliable sort of star. The kind that burns for about 10 billion years without doing anything particularly dramatic, fusing hydrogen into helium in its core, maintaining that great push and pull between gravity and energy, warming everything within reach. It has been doing this for about 4.6 billion years already. It has another 5 billion or so still to go. 5 billion years. Think about that for a moment. The entire history of life on Earth, from the first single-celled organisms floating in the primordial ocean, all the way through every extinction event, every evolutionary explosion, every fish that crawled onto land, every dinosaur that thundered across a Jurassic plain, every human being who has ever drawn breath, all of that fits comfortably inside the first half of our sun's life. We are, in stellar terms, a midlife species orbiting a middle-aged star. And when that remaining 5 billion years is up, when the hydrogen in the sun's core finally runs too low to sustain the fusion that keeps everything in balance, the sun will begin to change. It starts with the core. As the hydrogen supply dwindles, the outward pressure from fusion gently weakens. Gravity, which has been held at bay for billions of years, takes the opportunity to press inward just a little more firmly. The core compresses, gets hotter, and that additional heat causes something unexpected to happen to the outer layers of the star. They expand. Enormously. Dramatically. The sun swells outward like a slow, ancient breath being released, growing hundreds of times larger than it is today, its surface cooling and reddening as it stretches, transforming from the compact yellow star we know into what is called a red giant. This is, by any measure, a dramatic phase. The red giant sun will expand far enough to swallow Mercury, probably Venus, and almost certainly the Earth, though by that point, the Earth will have long since been rendered uninhabitable by the increasing luminosity of the aging sun, the oceans boiled away, the atmosphere stripped, the surface scorched to bare rock billions of years before the actual swallowing occurs. So let's not dwell on that part too long. The red giant phase is fiery and turbulent and rather spectacular, but it doesn't last in cosmic terms. It is a transition, a brief, brilliant upheaval between one phase of existence and the next. And then comes the letting go. A star like our sun, as it moves through and beyond the red giant phase, does something that I have always found quietly beautiful when I think about it properly. It releases itself. The outer layers, the vast, expanded, turbulent envelope of gas that the star swelled into during its red giant phase, begin to drift away. Not violently, not explosively, but gently, pushed outward by the radiation and stellar wind from the hot core within, expanding into space in a slow, graceful shell that astronomers call a planetary nebula. The name is a little misleading. These objects have nothing to do with planets. It was coined centuries ago by early astronomers who, peering through their telescopes, thought the glowing rings and disks resembled the circular appearance of planets. The name stuck, even though we now know they are something else entirely. Something far more interesting. A planetary nebula is, in a very real sense, a star's final gift to the universe. All that gas, the outer layers of a star that burned for billions of years, drifts outward into the surrounding space, glowing beautifully as it goes. Lit from within by the intense ultraviolet radiation pouring off the hot stellar core at the center. Sculpted by magnetic fields and stellar winds into rings and hourglasses and butterfly shapes and spirals, each one unique, each one a kind of portrait of the particular star that made it. The Helix Nebula, the Ring Nebula, the Cat's Eye Nebula, the Butterfly Nebula. These are the parting gestures of dying stars, and they are among the most breathtaking objects in the observable universe. But they don't last. Over tens of thousands of years, the gas disperses, thins, and fades. The colors wash out into the surrounding interstellar medium. The nebula becomes invisible. And what remains at the center, what was there all along, slowly being revealed as the outer layers departed, is the white dwarf. Let's spend a moment really sitting with what a white dwarf is, because it is a genuinely remarkable object. Imagine taking something roughly as massive as our entire sun, all of that material, all of that weight, and compressing it down to roughly the size of the Earth. Not the sun's size, the Earth's size. A sphere perhaps 12 or 13,000 kilometers across, containing the mass of a star. The density involved is staggering. We mentioned this briefly before, but it is worth returning to, because it genuinely stretches the imagination in a satisfying way. A single teaspoon of white dwarf material, just a teaspoon, the kind you'd stir your tea with, would weigh somewhere in the region of 5 to 15 tons here on Earth, depending on the particular white dwarf in question. A cubic meter of white dwarf material would weigh billions of kilograms. It is dense in a way that feels almost fictional, and yet it is real. We have observed thousands of white dwarfs. We understand them reasonably well. They are, in the current universe, quite common. In fact, it is estimated that roughly 97% of all stars will eventually become white dwarfs. Almost every star you see in the night sky tonight is destined for this fate. All those points of light, future white dwarfs, every one, waiting patiently for their time. But a white dwarf, for all its density, for all its compactness, is doing something quite different from the star it used to be. It is not fusing. That is perhaps the most important thing to understand about a white dwarf. The fusion has stopped. There is no more hydrogen burning in the core. No more helium igniting. No more nuclear fire of any kind. The white dwarf is not generating new energy. It is not producing light the way a living star produces light. What it is doing, and this is the key to everything, is simply cooling. Perhaps that is what we are doing tonight, in our own small way. Not burning. Just resting. Cooling gently into something quieter. There is no rush. The white dwarfs have been doing this for billions of years already. They know how. We need to talk about time. Not the kind of time we usually talk about. Not the kind that passes between waking up and going to sleep, or between one birthday and the next, or even between the rise and fall of great civilizations. We've already stretched past all of that. Already left those timescales far behind, somewhere back in the first few segments of this journey, like landmarks disappearing in a rear-view mirror. No, tonight we need to go further. Much further. We need to talk about time in quantities, so large that the numbers themselves become almost meaningless the moment you write them down. Numbers that the human brain, brilliant and curious and imaginative as it is, simply was not built to feel in any real, visceral sense. Numbers that you can understand intellectually, can repeat back without difficulty, and yet cannot truly grasp, not in the way you grasp that it's cold outside, or that it's been a long week, or that someone you love has been gone for 3 years now. These numbers are beyond feeling, beyond intuition, beyond analogy, almost. And yet we are going to try. Because if any process in the known universe deserves a patient, careful attempt at comprehension, it is this one. We are going to try to understand how long it takes a white dwarf to cool into a black dwarf. And the answer, when it comes, is going to be one of the most quietly staggering things you have encountered tonight. Let's begin by building a ladder. A ladder of time, with each rung representing a scale larger than the one below it, so that by the time we reach the top, or as close to the top as we're going, anyway, you have some sense of the distance we've climbed. The first rung. 1 year. Straightforward enough. 365 days. The time it takes the Earth to complete one full orbit of the Sun. You've lived through dozens of these. You know exactly how a year feels, the progression of seasons, the accumulation of small changes, the way December always seems to arrive faster than expected. The second rung. 1,000 years. A millennium. This is already beyond personal experience, but not beyond imagination. 1,000 years ago, the great cathedrals of Europe were being built. The Vikings were still raiding coastlines. The Aztec Empire hadn't yet risen. 1,000 years is history. Long history, history that requires books and archaeology to access. But it is still human history. Still full of people and stories and things we recognize. The third rung. 1 million years. 1,000 millennia. Here we leave recorded history entirely. 1 million years ago, our ancestors were early Homo species, chipping stone tools on the African savanna, not yet fully human in the way we'd recognize. The continents were in nearly their current positions, but glaciers covered vast swathes of the northern hemisphere. 1 million years is deep time, geological time, and it starts to feel genuinely vast. The fourth rung. 1 billion years. 1,000 million years. We are deep into geological and biological time now. 1 billion years ago, the most complex life on Earth was still single-celled. The oceans existed, but they were strange, different chemistry, different color, different everything. 1 billion years is most of the story of life on this planet. It is the kind of time in which continents are born and destroyed, in which oceans open and close, in which the entire character of a planet can change beyond recognition. The fifth rung. 13.8 billion years. The current age of the universe. Everything that has ever happened. The Big Bang, the formation of the first stars, the birth of galaxies, the formation of our solar system, the entire history of life on Earth, every human being who has ever lived, fits inside this number. This is, as far as we currently understand, the full span of cosmic history to date. Take a breath. Hold that number. Now let go of it, because we are about to leave it far, far behind. The sixth rung. 100 trillion years. This is 10,000 times longer than the current age of the universe. Written out, it looks like this, 100 followed by 12 zeros. 100 trillion years is, roughly, the expected total lifespan of the Stelliferous Era, the star-filled age we currently inhabit. This is how long it will take for the last stars to burn out, for the last embers of stellar fire to fade, for the universe to pass from its age of light into its age of darkness. 100 trillion years from now, the last star will die, and the white dwarfs will begin their long cooling in earnest. In the dark, in the silence, alone. Now, here is where it gets interesting. Here is where the numbers begin to do something that feels almost surreal. Because 100 trillion years, that vast, almost incomprehensible span that contains the entire future history of stars, is not even close to how long it takes a white dwarf to cool into a black dwarf. It is not even in the same conversation. 100 trillion years is, relative to the cooling timescale of a white dwarf, roughly equivalent to the first few seconds of a very long night. Let's talk about the actual numbers. Physicists, when they deal with timescales this large, have a sensible habit of writing them in what is called scientific notation, expressing numbers as powers of 10, rather than writing out all the zeros, because writing out all the zeros would be both impractical and faintly absurd. The current age of the universe, 13.8 billion years, can be written as approximately 10 to the power of 10. 10 with 10 zeros after it. That is our reference point. That is the age of everything we have ever known or observed. The end of the Stelliferous Era, 100 trillion years from now, is approximately 10 to the power of 14. For more zeros than the current age of the universe. Now, the cooling of a white dwarf. Early in the cooling process, say after the universe has aged to around 10 to the power of 15 years, a white dwarf that formed relatively recently will have cooled significantly. Its surface temperature will have dropped from the tens of thousands of degrees it started at, down towards something much lower. Cooler than any star that ever burned. Cooler than any world we know. But still not cold. Still not truly dark. Still radiating, barely, almost imperceptibly, into the surrounding space. 10 to the power of 15. That is 1 quadrillion years. 1 million billion years. It is 100 times longer than the entire Stelliferous Era. 100 times longer than the full lifespan of all the stars that will ever burn in this universe. And the white dwarf is still warm. Still cooling. Still not done. To become a true black dwarf. To cool to the point where it is, for all practical purposes, at the same temperature as the surrounding universe, indistinguishable from the cold dark space around it. A white dwarf needs significantly longer than that. Some estimates place the full cooling time at around 10 to the power of 17 years. Let's sit with that number for a moment, because it deserves the attention. 10 to the power of 17. That is a 1 followed by 17 zeros. 100 quadrillion years. Let's try to build a comparison, though I want to be honest with you from the start. Comparisons at this scale are imperfect. They are gestures toward understanding, rather than true comprehension. But they are worth making. The current age of the universe is roughly 10 to the power of 10 years. 10 to the power of 17 is 10 million times larger than 10 to the power of 10. So if the current age of the universe, 13.8 billion years of cosmic history, of stars being born and dying, of galaxies forming and colliding, of life arising on at least one small planet, and probably countless others. If all of that were compressed into a single second, then the full cooling time of a white dwarf into a black dwarf would be approximately 4 months. 4 months of seconds, each second representing the entire current age of the universe. That is how long this process takes. Or try it this way. The distance from the Earth to the nearest star, Proxima Centauri, our closest stellar neighbor, is about 4 light years. That means light, traveling at 300,000 kilometers per second, takes 4 years to cover that distance. It is an enormous distance by any human standard. The fastest spacecraft we have ever built would take tens of thousands of years to reach it. Now imagine a piece of paper. Standard paper, roughly 1/10 of a millimeter thick. If you folded that piece of paper in half 42 times, just 42 folds, it would be thick enough to reach from the Earth to the Moon. 42 folds. Now imagine folding it not 42 times, but enough times to represent the ratio between the current age of the universe and the cooling time of a white dwarf. The resulting stack of paper would reach not just to the Moon, not just to Proxima Centauri, not just across the galaxy. It would reach across a distance that makes our entire observable universe look like a single atom. The numbers are not just large. They are large in a way that compounds upon itself, again and again, until the mind simply lets go and floats. And I think that floating feeling, that gentle release of the attempt to truly grasp it, is actually where the peace lives, in these timescales. You stop trying to hold it, and you just let it be large. Incomprehensibly, serenely, almost comfortingly large. There is a reason this is sometimes described as one of the slowest processes in all of known physics. Physics is full of slow processes. There are radioactive isotopes that decay over billions of years. There are geological processes, the movement of tectonic plates, the erosion of mountain ranges, that unfold over timescales utterly invisible to human experience. There are processes so slow that detecting them at all requires instruments of extraordinary sensitivity, measurements taken over years and decades, just to register a change too small to see. But the cooling of a white dwarf into a black dwarf sits in a different category entirely. It is slow in the way that only cosmological processes can be slow. Slow in a way that makes geological time look frantic. Slow in a way that makes the lifespan of the universe itself seem brief by comparison. And what makes it particularly remarkable, particularly worth pausing over, is that it is not slow because nothing is happening. It is slow because of the sheer scale of the task involved. A white dwarf is not a small object. It contains, remember, roughly the mass of an entire star, compressed into a sphere the size of a planet. The amount of thermal energy stored inside a newly formed white dwarf is almost beyond reckoning. It is the accumulated heat of billions of years of nuclear fusion, compacted into an incredibly dense object with an incredibly small surface area relative to its mass. And that heat has to get out through that surface. Not all at once. Not in a rush. One photon at a time, in a sense. Energy radiating from the surface into the surrounding space, carrying a tiny fragment of the white dwarf's warmth away with it, leaving the object ever so slightly cooler than it was before. One photon at a time. For 10 to the power of 17 years. There is something almost meditative about that image, if you let yourself sit with it. A white dwarf, alone in the dark. Long after the stars have gone out. Long after the galaxies have dispersed. Long after anything we would recognize as the living universe has faded into memory. Just this dense, ancient, patient sphere, slowly, so slowly, releasing the heat it accumulated during its long, bright, burning life. Not in a hurry. Not capable of being in a hurry, really. The physics simply doesn't allow it. The rate at which heat can escape from a white dwarf is governed by laws that cannot be rushed, cannot be circumvented, cannot be persuaded to move faster. The cooling will happen at exactly the rate the cooling happens, and nothing in the universe can change that. There is, I think, something unexpectedly comforting in that. We live in a world that is always accelerating, always asking more, faster, sooner. Where patience is a virtue people speak about in theory, but find difficult to practice. Where slowness is often treated as a failing rather than a quality. And here, out in the deep future of the universe, is a process so slow that it makes all of our urgency look like a brief, bright flicker. A process that simply does what it does, at the pace it does it, for a length of time that dwarfs all of recorded history many billions of times over. The white dwarf does not mind the wait. It has no concept of waiting. It simply is what it is, cooling at the rate it cools, releasing its warmth photon by patient photon, for a span of time that none of us, no human being who has ever lived, no civilization that has ever risen, no mind that has ever turned its attention to the stars, will ever witness from beginning to end. And at the end of it, at the conclusion of this extraordinary, almost infinite slow exhale of heat into the darkness, what is left? A black dwarf. An object that looks, from the outside, almost identical to the white dwarf it came from. Same size, same mass, same dense, compact sphere. But cold now. Truly cold. Dark. Invisible. Radiating nothing. Not in the visible spectrum. Not in infrared. not in any wavelength of light that carries meaningful energy. Just matter. Ancient, patient, enduring matter. A fossil of a star. A memory, in physical form, of something that once burned brightly enough to warm a solar system, to sustain life, perhaps, on any worlds that happen to be orbiting at the right distance. A memory that will persist, in that dark and silent universe, for longer still. Because a black dwarf, once formed, is in no hurry to go anywhere either. But we are getting slightly ahead of ourselves. Before we arrive fully at the Black Dwarf Era, before we settle into that final, deep, dark chapter of the cosmos, there are a few more things to understand. A few more extraordinary processes to witness. The universe, even as it grows old and cold and quiet, has a few more remarkable stories to tell. And we have time to hear them. All the time, in fact, that there is. So rest here for a moment, in the enormity of what we've just considered. Let the numbers dissolve. They were never really meant to be held, only to be gestured toward, like pointing at a star you cannot quite name. Just feel the scale of it vaguely around the edges. A universe growing old. A white dwarf cooling. A process so slow it makes time itself seem patient. And somewhere, impossibly far ahead, the darkness settling in. Gently, without any rush at all. We have established, by now, that white dwarfs cool slowly. Extraordinarily slowly. Timelessly slowly. Slowly in a way that makes the entire current age of the universe look like an impatient fidget, a brief drumming of fingers on a table, before the Rayol waiting begins. But I want to go a little deeper tonight, because when I say the white dwarf cools, when I use that simple, clean, ordinary word, cools, I am, in a sense, doing the process a disservice. I am making it sound straightforward, linear, uneventful, as though cooling is simply a matter of being warm, and then being slightly less warm, and then being slightly less warm again, in a smooth and unbroken progression toward cold. It isn't like that. Not exactly. The cooling of a white dwarf is more like a story than a single event. It has chapters. It has shifts in pace, moments of acceleration, moments where the process almost seems to pause and reconsider itself. It has a phase, a genuinely remarkable phase, where the white dwarf, in a sense, pushes back against its own cooling, where the physics of the object itself slows the process down, releasing stored energy in a way that temporarily warms things back up, before the inevitable cooling resumes. It is a long, slow, complicated exhale, and like all long, complicated exhales, it is worth paying attention to. Let's begin at the beginning. At the moment a white dwarf is first born, the planetary nebula has dispersed. The outer layers of the dying star have drifted away into the surrounding space, glowing briefly and beautifully before thinning into invisibility. And at the center of what was once a living, burning star, the core sits exposed, dense, compact, unimaginably hot. How hot? In the first moments of a white dwarf's existence, the surface temperature can exceed 100,000 degrees. Some newly formed white dwarfs are hotter than that, significantly hotter. They blaze in the ultraviolet spectrum, pouring out radiation at wavelengths far beyond what human eyes can detect. They are, despite being dead in the sense of no longer fusing, still among the hottest objects in their immediate cosmic neighborhood. And they need to cool from that, from 100,000 degrees or more, all the way down to the temperature of the surrounding universe, which, in the deep future we are journeying toward, will be just a fraction of a degree above absolute zero. The distance between those 2 points, the starting temperature and the ending temperature, is vast. And the journey between them is not a simple straight road. It is, instead, a series of very different landscapes. The first landscape is perhaps the most counterintuitive, because in the earliest phase of a white dwarf's cooling, in those first relatively brief millions and billions of years, the dominant mechanism carrying energy away from the object is not light. It is neutrinos. Neutrinos are among the most ghostly particles in all of physics. They have almost no mass, so little mass that for a long time physicists thought they had none at all. They carry no electrical charge. They interact with ordinary matter so weakly that they can pass straight through the entire Earth, through rock and iron and ocean, through the molten core and out the other side, without interacting with a single atom. Billions of neutrinos are passing through your body right now, at this very moment, as you listen to this. They are completely harmless, completely undetectable to your senses, almost completely undetectable to our most sensitive instruments. And yet, in a young, extraordinarily hot white dwarf, neutrinos are produced in enormous quantities, generated by the intense thermal activity within the densely packed interior. And because they interact so weakly with matter, they do something that light cannot do. They escape directly from the core. Light, by contrast, has a much harder time getting out. The interior of a white dwarf is so dense that a photon of light, a particle of electromagnetic radiation, cannot simply travel from the center to the surface in a straight line. It gets absorbed and re-emitted, deflected and scattered, over and over again, bouncing through the dense interior on a slow, complicated, wandering journey that can take an extraordinary length of time. Light is, in a sense, trapped inside the white dwarf, leaking outward only very gradually. But neutrinos? They simply leave. Immediately. Carrying their energy with them. Straight through the dense stellar material, as though it weren't there at all. Out into the surrounding space at nearly the speed of light. In the early phase of a white dwarf's life, this neutrino cooling, this steady stream of ghostly particles carrying thermal energy directly out of the core, is actually the dominant cooling mechanism. More heat is lost to neutrinos than to the light glowing from the surface. This phase doesn't last forever. As the white dwarf cools and its internal temperature drops, the production of neutrinos slows dramatically. Eventually, neutrino cooling becomes negligible, a whisper rather than a rush, and the white dwarf transitions into its second great cooling phase. The second landscape is, in some ways, the most familiar, because now the white dwarf is cooling the way most hot things cool, by radiating heat from its surface. This is thermal cooling, and it is, at its heart, the same process by which a cup of tea cools on a table, or a stone left in a warm room gradually releases its warmth into the surrounding air. Heat moves from hotter places to cooler ones. The surface of the white dwarf is hot. The space around it is cold. And so, photon by patient photon, heat flows outward. The white dwarf glows. Faintly, in the context of the universe, nothing like the blazing luminosity of a living star, but consistently, steadily, releasing its surface heat as light, mostly in the visible spectrum at first, then shifting toward the red and the infrared as the surface cools over billions of years. This thermal cooling phase is, in terms of raw timescales, the longest of the early stages. It proceeds slowly, reliably, and without dramatic interruption. The white dwarf grows cooler by degrees, very, very slowly by degrees, and astronomers observing it from a distance might, over the course of billions of years, watch its color shift. White to yellow, yellow to orange, orange to deep, dull red. But there is something happening inside the white dwarf, during all of this surface cooling, that is not at all simple or uneventful. Something that will, in fact, interrupt the process in a rather remarkable way. Beneath the surface of the white dwarf, deep inside its extraordinarily dense interior, the material is doing something that material at these densities and temperatures does, and that we have observed and confirmed, and found genuinely surprising the first time we understood it properly. It is beginning to freeze. Now, I want to be careful with that word, freeze, because it carries connotations that don't quite fit here. When we think of things freezing, we tend to think of water turning to ice, of cold temperatures causing liquids to solidify. And while the physics of white dwarf crystallization shares some resemblance to freezing in that general sense, the details are very different and very strange. The interior of a white dwarf is made primarily of carbon and oxygen, the ash, essentially, of billions of years of nuclear fusion. At the extraordinary densities inside a white dwarf, this material doesn't behave the way carbon or oxygen behaves in any environment we have direct experience of. It exists in a state called a Coulomb plasma, ions of carbon and oxygen moving through a sea of electrons, the whole thing behaving in ways that depend delicately on both temperature and density. As the white dwarf cools, there comes a point, a specific temperature threshold, at which the thermal energy of the ions is no longer sufficient to keep them moving freely past one another. They begin to settle, to arrange themselves. The ions, under the influence of their mutual electrical repulsion and the confining pressure of the surrounding material, lock into a regular, ordered lattice structure. A crystal. The interior of the white dwarf literally crystallizes. From the center outward, the carbon and oxygen ions arrange themselves into something resembling an enormous, incredibly dense crystal lattice. Not ice, not anything we have a familiar name for, but a genuinely crystalline structure, ordered and regular, spreading through the interior of the dead star over millions of years. We have evidence for this. Real, observational evidence. Astronomers studying certain white dwarfs have found signatures consistent with large-scale crystallization. Populations of white dwarfs that appear to be cooling more slowly than expected, as though something is releasing energy inside them and slowing the process down. And that is exactly what is happening. Here is the part that I find most extraordinary about this entire process. The part that, when I first encountered it properly, made me stop and read it again slowly. Crystallization releases heat. When the ions inside a white dwarf lock into their crystal lattice, when that phase transition occurs, as the interior shifts from a disordered plasma to an ordered crystalline solid, energy is released. Latent heat, physicists call it. The same phenomenon, in principle, as the heat released when water freezes into ice. The ordering of the system, the transition from disorder to order, releases energy that temporarily flows back into the white dwarf, warming it slightly from within. The white dwarf, in the process of freezing, warms itself up. Not dramatically. Not enough to restart any fusion. Not enough to make it suddenly shine brightly again after billions of years of cooling. But measurably, detectably, in ways that slow the overall cooling process, that introduce a kind of pause, or at least a significant slowdown, into what might otherwise have been a steadier, uninterrupted decline. The white dwarf pushes back, in a sense, against its own cooling. Not intentionally, of course. There is no intention here, no will, no preference. Just physics, doing what physics does, following laws that have no interest in our narratives or metaphors. But the result, from our storytelling perspective, is something that feels almost like resistance. Almost like the last warmth of something ancient refusing to go quietly. This crystallization phase plays out over billions of years. Slowly, the crystal front moves outward from the core toward the surface, locking more and more of the interior into its ordered lattice, releasing its latent heat as it goes. And during this time, the white dwarf cools more slowly than it otherwise would. The crystallization essentially donates energy back into the cooling budget, extending the process, stretching it out even further than the already extraordinary timescales we've been discussing. It is, in a very deep sense, a star taking its time. But eventually, because eventually is the word that governs everything in the universe, given enough of it, the crystallization is complete. The entire interior of the white dwarf has locked into its crystal lattice. Every ion has found its place in the ordered structure. The latent heat has been fully released and radiated away. And the white dwarf, now essentially a solid crystal sphere, a diamond, in a loose sense, though the chemistry is more complex, must continue its cooling by other means. And this is where we enter the fourth and final landscape, the strangest and most drawn-out phase of all. It is called Debye cooling, named after the Dutch physicist Peter Debye, who developed the theoretical framework for understanding how crystalline solids lose heat at very low temperatures. In most objects, as temperature drops, the rate of cooling slows. Cooler things cool more slowly than hotter things. A cup of lukewarm water cools more slowly than a cup of boiling water. This is familiar and intuitive. But in crystalline solids, as the temperature drops toward the very low end of the scale, something more extreme happens. The ability of the crystal to carry and release heat drops off dramatically, far more sharply than in simpler materials. The vibrations that carry thermal energy through a crystalline solid, called phonons, the quantum mechanical equivalent of sound waves, become increasingly suppressed at very low temperatures. There are fewer of them. They carry less energy. The crystal becomes, in a deep physical sense, increasingly incapable of efficiently releasing the small remaining heat it contains. And so the cooling slows. Not just gradually slows. It slows in a way that becomes more and more extreme the colder the white dwarf gets. The final fraction of warmth is the hardest to release. The last degrees above absolute zero take longer to shed than all the previous cooling combined, in some respects. The process becomes agonizingly, almost incomprehensibly slow, even by the already extraordinary standards of everything that came before it. This is the phase that stretches the total cooling time out to those staggering figures we discussed in the last segment. To 10 to the power of 15, 10 to the power of 17 years. The Dubai cooling phase is where most of that time lives. In the final, infinitesimal release of the last residual warmth from an ancient crystalline, almost perfectly cold sphere drifting in a dark and silent universe. I want to take a moment here, before we move on, to just appreciate what we've been describing. We've been talking about a process that begins with a blazing hot stellar remnant, radiating fiercely in the ultraviolet, streaming ghostly neutrinos directly out of its core. And we've watched it, in our imagination, pass through phase after phase. Neutrino cooling, thermal cooling, crystallization, Dubai cooling. Each phase distinct, each one slower and stranger than the last, each one a different chapter in the same extraordinarily long story. And we've watched the white dwarf change throughout. Not just in temperature, but in its very internal structure. The disordered plasma of its youth. Ions moving freely through a sea of electrons, slowly giving way, deep inside, to the perfect ordered lattice of a crystal. The star, in its old age, becoming something almost gem-like at its core. A sphere of crystallized carbon and oxygen, ancient and dense and dark, drifting through a universe so cold and so empty that the distinction between being warm and being cold has become almost philosophical. There is an image I keep returning to when I think about this. A geode. One of those rough, unassuming rocks that, when broken open, reveals a hollow interior lined with perfectly formed crystals, purple amethyst, or clear quartz, or sparkling pyrite. Something that looks ordinary on the outside and contains, within it, a hidden order, a hidden geometry, a hidden beauty that took an enormous amount of time and pressure to form. A white dwarf, in its crystallized final phase, is something like that. Unremarkable from the outside, perhaps just a dark, cold, invisible sphere in the deep black of an empty universe. But inside, if you could somehow look, an ordered structure of extraordinary density and regularity. A crystal the size of a planet. A gem made of the compressed heart of a star. There is something lovely about that, I think. Something that rewards the patience required to understand it. So the white dwarf cools. Stage by stage. Phase by phase. Neutrinos rushing away in the early heat. Light leaking slowly from the surface over billions of years. The interior crystallizing from the inside out, releasing its latent warmth in a long, slow donation back to the cooling budget. And finally the Dubai phase. That extraordinary, glacial endgame where the last traces of warmth drain away with agonizing slowness from a crystalline sphere that has already been cooling for longer than the current universe has existed. And at the very end of all of that, darkness, stillness, a black dwarf, fully cooled, fully crystallized, fully dark, as cold as the universe around it, which by now, in the unimaginably far future when this process completes, will itself be extraordinarily cold. The temperature of the cosmos has been dropping since the Big Bang, and by the time the last white dwarfs become the first true black dwarfs, the background temperature of the universe will be almost indistinguishable from absolute zero. Cold meeting cold. Dark meeting dark. And yet, and this is important, and we will return to it, the black dwarf is still there. Still present. Still a physical object, occupying space, possessing mass, exerting the gentle pull of gravity on anything nearby. It has not dissolved. It has not evaporated. It has not ceased to exist. It is simply resting. In the deepest, most complete sense of the word. Resting in the dark, in the cold, in the silence of a universe that has grown very, very old. And in that resting, in that patient, crystalline stillness, there are still, incredibly, a few more chapters left to tell. But those are for later. For now, let the image settle. A crystal sphere in the dark. Ancient beyond all reckoning. Cold. Still. Alone. And yet, in its own quiet way, enduring. There is no explosion. No flash of light. No shockwave rippling outward through the surrounding space. No dramatic final moment that you could point to and say, "There, that was it. That was the moment it happened." The birth of a black dwarf is not like that at all. In fact, calling it a birth feels almost paradoxical, because what we are describing is, in the most literal sense, the end of something. The conclusion of a process that began when a star first collapsed into a white dwarf, perhaps trillions of years before. The final page of an extraordinarily long chapter. And yet it is also, unmistakably, the beginning of something else. Something new. Something that has never existed before in the history of the universe. Because, as we have established, not one true black dwarf exists yet. Not anywhere. Not in the entire observable cosmos. The first black dwarf will be the first of its kind. Ever. And its arrival will be marked by nothing more dramatic than the absence of something that was already almost imperceptible. The last faint whisper of warmth, fading into silence. That is all. That is everything. Let's stay with that image for a moment, the final cooling. Because I think it deserves more than a passing mention. I think it deserves to be felt, or as close to felt as these extraordinary timescales allow. Imagine the white dwarf as it exists in its final phase. We've already traced its journey. The early neutrino cooling, the long slow thermal radiation, the crystallization spreading inward to out, the deep Dubai cooling phase where the last traces of warmth become almost impossibly slow to release. By this point in its existence, the white dwarf is already ancient in a way that beggars description. It formed, perhaps, when the universe was a few billion years old, in the Stelliferous Era, when stars still burned and galaxies still glowed, and there was light everywhere you looked. That was so long ago that the universe has since aged past the death of every star, past the dispersal of galaxies, past the end of the age of light entirely. The white dwarf has been cooling in the dark for longer than stars existed, longer than galaxies existed, longer, in all likelihood, than most of the processes we think of as defining the universe have been active. It is a relic, a fossil, a remnant of a time so distant that nothing else from that era remains visible, or active, or warm. And it is almost cold now. Almost. The temperature of its surface, once measured in hundreds of thousands of degrees, has dropped to something barely above the temperature of the surrounding universe. Not zero. Not quite. But close. Approaching. The gap between the white dwarf's temperature and the background temperature of the cosmos has narrowed to something so small that measuring it would require instruments of extraordinary sensitivity. Instruments that, in this cold, dark, ancient future universe, may not exist anywhere. There may be no one to measure it. There may be no one at all. And then, at some point at no particular dramatic moment, in no particularly special location, with no audience and no ceremony, and no record being kept by anyone, or anything the last photon leaves. Not the last photon in the universe. Not anything so grand as that. Just the last meaningful photon from this particular object. The last quantum of energy that carries away the final measurable trace of the white dwarf's warmth. The last connection, however tenuous, between this ancient compressed sphere and the concept of heat. It departs at the speed of light, as all photons do, heading outward into the surrounding darkness in a straight line that will carry it, unimpeded, for an essentially infinite distance through a universe that has grown too cold and too empty to absorb it. And in the moment after that photon leaves, though moment is almost too small a word for what we mean here, the object it came from is something new. It is a black dwarf. Not warm. Not cool. Not fading. Just cold. Genuinely, completely, thoroughly cold. Indistinguishable in temperature from the space surrounding it. radiating nothing into that space, no light, no infrared, no heat signature of any kind. To any detector you could imagine, pointed at the space where this object sits, the reading would be the same as pointing that detector at empty space. The black dwarf is, for almost all practical purposes, invisible. But it is not nothing. This is the thing I most want to make clear, the thing that I find most quietly astonishing about black dwarfs, the thing that separates them from simply ceasing to exist. A black dwarf is still there. It still occupies space. It is still a physical object, with physical dimensions roughly comparable to a planet, perhaps 12 or 13,000 kilometers across, in the case of one that formed from a sun-like star. It still possesses mass roughly the mass of a star, compressed into that planet-sized sphere. It still exerts gravity on anything that happens to be nearby, that same gentle, patient gravitational pull that held planets in their orbits when this object was a living star, that continued to hold them when it became a white dwarf, and that continues still, now, in the deep cold silence of its final form. If you were somehow transported to the vicinity of a black dwarf, if you found yourself floating in the space near one of these ancient, invisible objects, you would not see it. Not directly. There is no light coming from it to see. But you would feel its gravity. Very gently, imperceptibly almost, depending on your distance, but it would be there. A slight, persistent tug. A gravitational whisper from an object that has otherwise gone completely silent. And if you somehow knew where to look, if you had instruments sensitive enough to measure the faint gravitational lensing, the barely perceptible bending of background light around the object's mass, you might be able to infer its presence. Deduce that something is there, even if you cannot see it. Like knowing a word is missing from a sentence, not because you can see the word, but because the sentence doesn't quite work without it. The black dwarf is the missing word. Present in the space it occupies, in the gravity it exerts, in the crystalline structure it has preserved through trillions of years of patient cooling. Just not visible. Just not warm. Let's think about what the black dwarf actually is, in those final terms. What it is made of, and what that means. The interior, as we explored in our last segment, is crystallized. The carbon and oxygen ions that make up the bulk of the white dwarf have long since locked into their regular lattice structure, a crystal of extraordinary density and size, compressed under pressures that nothing in our everyday experience can approach. The crystallization that began in the core and spread outward over billions of years is now complete. The entire object, from its center to its surface, is solid crystal. Not crystal in the way we usually mean, not a delicate, translucent thing you might find in a shop window or hold up to the light. Dense crystal. Incomprehensibly dense. A crystal in which every ion is held in place by forces so powerful that nothing short of a catastrophic collision or an extraordinary gravitational event could disrupt the structure. Some physicists, when trying to describe the crystallized core of a cooling white dwarf, reach for the word diamond. The comparison is imperfect, the chemistry is more complex. The pressures involved far exceed anything that produces diamonds on Earth, and the structure is not exactly the same, but the spirit of the comparison is useful. There is something diamond-like about it. Something hard, and ordered and cold, and permanent feeling. A black dwarf is, in a loose and approximate but evocative sense, something like an enormous diamond the size of a planet, made of the compressed heart of a dead star, drifting invisibly through the cold dark of a universe that has grown so old it barely remembers what stars were. I find that image genuinely beautiful. I hope you do too. Now, the name itself. Black Dwarf. It is a straightforward name, really. Practical. Descriptive. It tells you what you need to know. That this object is in the dwarf category, that small but massive family of stellar remnants of which white dwarfs are the most familiar, and that it is black. Dark. Not emitting light. But there is a certain poetry in it, I think, if you let there be. Black, in the context of light and physics, means the absorption of everything and the emission of nothing. A perfect black body, in the theoretical physics sense, is one that absorbs all radiation that falls on it and reflects none back. A black dwarf, in the deep future of the universe, is not even absorbing much, because there is very little radiation left in the cosmos to absorb. It is black in the most complete sense, the most absolute sense. Black not because it is consuming light, but because it is neither producing nor reflecting any. It is, you might say, the darkest kind of dark. And dwarf, that word carries its own quiet weight. Dwarfs, in astronomy, are the small survivors, the compact remnants, the ones who outlast the giants. White dwarfs will outlast neutron stars in terms of sheer endurance. Black dwarfs will outlast almost everything. In the taxonomy of stellar remnants, dwarf implies not weakness but persistence, not smallness but density, not limitation but a kind of concentrated, indestructible endurance that the larger, more dramatic objects cannot match. The black dwarf is the final survivor of stellar evolution, not the most dramatic endpoint a star can reach. That distinction belongs to black holes, those extraordinary singularities of compressed spacetime. But in terms of sheer persistence, in terms of the simple refusal to cease existing, the black dwarf is remarkable. It will still be there when almost everything else has changed beyond recognition. And here is something I want to dwell on for a moment, because I think it gets to the heart of what makes black dwarfs so quietly extraordinary as objects of contemplation. There is a tendency, when we talk about the deaths of stars, to reach for dramatic language. Stars explode. They collapse. They go supernova in brilliant, violent outbursts that briefly outshine entire galaxies. They implode into neutron stars, objects so dense that a single teaspoon would weigh billions of tons, spinning hundreds of times per second, radiating beams of energy across the cosmos like cosmic lighthouses. They collapse further into black holes, singularities where our understanding of physics breaks down entirely, where space-time curves so severely that not even light can escape. These are dramatic endings. Endings worthy of the word dramatic. Endings that announce themselves loudly across the universe. But a black dwarf does none of this. A black dwarf simply fades. Gradually. Quietly. Without announcement or ceremony. The light dims over trillions of years, the way a very distant sound dims as you walk away from it. Not all at once, not with any clear boundary between audible and inaudible, just slowly, gradually becoming less and less present until the question of whether you can still hear it becomes indistinguishable from the question of whether it was ever there at all. And then it is cold. And then it is dark. And then it is a black dwarf. There is something in this quiet ending that I find more moving, in a certain way, than the dramatic ones. The supernovae are spectacular. The neutron stars are extraordinary. The black holes are genuinely mind-bending. But the black dwarf, the end point of the most common type of stellar death, the fate of the vast majority of all the stars that will ever exist, goes out like a light that has simply been on for so long, through so many dark nights, that it has quietly exhausted itself. Not in failure, not in violence, just in the most complete, unhurried kind of rest. It is not dead in a dramatic way. It has simply finished being what it was, and settled into something quieter. Think about all the stars whose light we see when we look up at the night sky tonight. Every single one of those points of light, every star visible to the naked eye, every star in the photographs from our great space telescopes, every star in every galaxy of the hundreds of billions of galaxies in the observable universe. The vast majority of them are destined for this. Not for the spectacular violence of the supernova, not for the exotic extremity of the neutron star or the black hole, but for the long, patient, quiet journey from star to white dwarf to black dwarf. They will burn their hydrogen. They will swell into red giants. They will shed their outer layers in beautiful, brief planetary nebulae. They will spend trillions upon trillions of years, slowly cooling in the dark. And eventually, long after anything we can currently comprehend has passed, they will arrive at the same destination. Cold, dark, crystalline, still. All of them, every one, ending the same quiet way. Not with a bang. Not with drama. Just with that final fading, that last photon departing into the dark, that almost imperceptible transition from almost cold to cold. From white dwarf to black dwarf. From something to something so quiet it is almost nothing. But not nothing. Never quite nothing. There is a quality that black dwarfs possess. This quality of being present without being visible, of existing without announcing themselves, of persisting in the dark long after the universe has largely forgotten what light was, that I find unexpectedly peaceful to contemplate. We live in a world that rewards visibility, that tends to equate presence with brightness, significance with loudness, importance with the ability to be noticed. The things we celebrate are the things that shine. But the black dwarf shines not at all, and it endures longer than almost anything. It does not need to be seen to be real. It does not need to be warm to persist. It simply exists, in the patient and unhurried way that only the very dense and the very cold can exist. Settled into itself, complete, requiring nothing from the universe around it, and offering nothing back except the quiet fact of its presence, the gentle pull of its gravity, the crystalline order of its interior, the memory, locked into its very structure, of a star that once burned. We have arrived, now, at the thing this entire journey has been building toward. We have traced the life of a star from birth to death. We have watched it collapse into a white dwarf and begin its long, extraordinary cooling. We have explored the stages of that cooling, the neutrino rush, the thermal glow, the crystallization, the Dubai endgame. We have watched the light dim, degree by degree, trillion year by trillion year, until the last photon departs and the object crosses that quiet threshold into something new. We know what a black dwarf is now, not just as a definition, but as a thing with texture and history and a kind of beauty that rewards the patience required to understand it. And now we can ask the next question. The question of what the universe looks like when it is full of them. When the last star has gone out and the last white dwarf has cooled and the cosmos is populated by these silent, dark, crystalline remnants drifting through a cold and ancient space. What is that universe actually like? What is still happening, out there in the dark? Because something is. Even then, even in the deepest cold of the Black Dwarf Era, the universe has not entirely finished its story. There are still, incredibly, a few last things to tell. But for now, let this moment be enough. The birth of a black dwarf. Not announced, not witnessed, not dramatic, just a quiet arrival into darkness. A settling, a rest so deep and so complete that the universe itself can barely tell the difference between this ancient, crystalline sphere and the cold space surrounding it. But it is there, patient and cold and enduring. In the dark. Step back, not just a little, not just to the edge of our solar system, or to the outskirts of our galaxy, or even to the furthest reaches of what our telescopes can currently see. Step back all the way, as far back as perspective allows, until the individual objects, the white dwarfs, the black dwarfs, the scattered remnants of what were once stars become too small and too distant to pick out individually. Until what you see is not objects, but the universe itself. The whole of it, or as much of the whole as any vantage point can offer. Look at it from out here, and tell me what you see. Nothing, or rather almost nothing. The suggestion of something, perhaps. A vast, three-dimensional darkness, stretching outward in every direction without boundary or edge, without center or horizon. A darkness so complete and so uniform that the word darkness doesn't quite do it justice, the way the word large doesn't quite do justice to the distance between galaxies. This is the universe of the Black Dwarf Era, seen whole. And it is dark in a way that the universe has never been dark before. Not the darkness of a moonless night on Earth, where the stars still wheel overhead and the Milky Way still arches across the sky in its pale, luminous band. Not the darkness of deep space as we know it now, where even in the void between galaxies, there is always somewhere, always some direction you can point where a faint smudge of light betrays the presence of a distant galaxy, a distant star, a distant source of warmth. Not even the darkness of the period just after the Big Bang, before the first stars ignited, that was a warm darkness, a dense darkness, full of energy and possibility, and the seeds of everything that was to come. This darkness is different. This darkness is the darkness of aftermath, of conclusion, of a universe that has spent an almost incomprehensible span of time using up its reserves of light and heat and stellar fire, and has now arrived at the other side of all of that. A universe that has, in the most fundamental sense, grown old. And like many things that grow old, it has grown quiet. To understand what this universe looks like, or rather, what it doesn't look like, it helps to remember what the universe looked like at its most alive. There was a period, a few billion years after the Big Bang, that cosmologists sometimes call cosmic noon. The universe was younger then, and denser, and the rate at which new stars were forming across all its galaxies was at its peak. Galaxies everywhere were blazing with the light of newborn stars, hot, blue, brilliant young stars forming from collapsing clouds of gas at a rate that makes our current universe look subdued by comparison. Cosmic noon. A universe ablaze with star formation. Every galaxy a furnace of new light. It was the brightest the universe has ever been, or ever will be. And from that peak, the rate of star formation has been declining ever since. Not dramatically, not suddenly, but steadily the available gas being used up, converted into stars, and then into stellar remnants, the raw material of new suns gradually depleted. Our current universe, 13.8 billion years after the Big Bang, is already well past cosmic noon. The rate of star formation today is a fraction of what it was at the peak. The universe is already, in a sense, dimming, though so slowly that no human lifetime could detect it. The dimming will continue. Over hundreds of billions of years, over trillions of years, it will continue, each generation of stars using up a little more of the available gas, each stellar death leaving behind a remnant that contributes no new light, until eventually the gas runs too thin, the clouds too dispersed, and new star formation simply stops. Not with a declaration. Not with any clear moment you could identify as the last star being born. Just with a gradual trailing off, a slowing of the rate until the rate becomes effectively zero. The last star will form somewhere, at some point, and it will not know it is the last. There will be no ceremony. Just a cloud of gas collapsing, a new star igniting, and then after that particular star has burned out, no more. The furnace cooling. For the last time. Forever. Now imagine the universe after that. After the last star has formed. After the last star has burned through its fuel, and shed its outer layers, and collapsed into its white dwarf remnant, and begun its long, patient cooling. The galaxies are still there, in a sense. Or at least, the structures that were galaxies are still there. The gravitational scaffolding that held them together, the dark matter halos, the accumulated mass of billions and billions of stellar remnants still exists. But the galaxies as we know them, as luminous structures, as the great glowing wheels and ellipses and irregular clouds of stars that define the visual character of our universe, those are gone. Where once a spiral galaxy turned slowly in the dark, trailing its arms of blue and white and golden stars, there is now a diffuse collection of dark remnants. Black dwarfs, mostly the cooled and darkened cores of the average stars that once populated the galaxy. Neutron stars, here and there the denser remnants of more massive stars that ended their lives in supernovae rather than planetary nebulae. Black holes, sitting at the centers where they always sat, still enormous, still patient, still drawing anything that ventures too close into their gravity wells with quiet, implacable persistence. And perhaps, scattered through the remnant structure, a handful of brown dwarfs. Failed stars, objects that formed from collapsing gas clouds, but never accumulated quite enough mass to ignite fusion. These dim, cool, Jupiter-like objects were never bright to begin with, and they will persist for extraordinary lengths of time simply because they consume so little and demand so little from the universe around them. But none of these things glow, in any meaningful sense. None of them light the galaxy. The galaxy is dark. Let's talk about what darkness of this completeness actually means for the universe as a whole. Right now, in our universe, light is everywhere. Not just from stars, from everything. Every hot object emits radiation. The cosmic microwave background, the faint afterglow of the Big Bang itself, fills all of space with a uniform, extremely faint warmth. Galaxies pour out light across the full electromagnetic spectrum, from radio waves to gamma rays. Quasars blaze at the centers of distant galaxies with luminosities that dwarf entire star clusters. Even the spaces between galaxies glow faintly with tendrils of hot gas. Light, in our universe, is not the exception. It is the medium. It is what the universe communicates in. It is how everything knows about everything else. How gravity's effects propagate, how we observe, how the story of one part of the cosmos is written in the sky of another. In the Black Dwarf Era, this changes completely. The cosmic microwave background, that faithful, omnipresent afterglow, will have continued its billions of years-long cooling until it is, even by the already frigid standards of the deep universe, extraordinarily cold. Its temperature, already just a few degrees above absolute zero today, will have dropped to something so close to absolute zero that the distinction between them is essentially academic. The galaxies are dark. The stars are gone. The hot gas that currently fills galaxy clusters has long since cooled and dispersed. Even the relatively active events, supernovae, the formation of new stars, the spectacular collisions of neutron stars, belong to the vanished past, to that impossibly distant era of light and warmth that was the Stelliferous Age. What remains is a universe communicating in almost nothing. Almost but not quite silence. Because the universe, even in the Black Dwarf Era, is not entirely static. Gravity is still working. Gravity, unlike light, unlike heat, unlike the nuclear forces that powered the stars, gravity doesn't run out. It doesn't cool. It doesn't fade. It is simply there, always, an intrinsic feature of mass and spacetime, operating at every scale from the subatomic to the cosmic, persistent and patient in a way that outlasts almost everything else. And in the Black Dwarf Era, gravity is really the only significant player left. What does it do in a universe full of cold, dark remnants? It does what it has always done. It pulls things together. Slowly, over extraordinary timescales, the black dwarfs and neutron stars and other remnants, within what were once galaxies, continue to interact gravitationally. They don't interact dramatically. There are no stellar collisions happening every second, no bright nebulae being compressed into new suns. But they interact. Over billions and trillions of years, these gravitational interactions gradually nudge objects in various directions. Some objects are flung outward, toward the edges of the galactic remnant and beyond, escaping into the vast intergalactic dark. Others sink inward, drawn by successive gravitational encounters toward the center, toward the supermassive black hole that sits there, patient and enormous, waiting. The process, called gravitational relaxation, operates on timescales that dwarf even the cooling times of white dwarfs. But it operates. The remnant galaxies are not frozen in place. They are evolving, slowly, their populations of dark remnants, slowly reorganizing themselves under the quiet governance of gravity. Very occasionally, by which I mean on timescales of trillions or quadrillions of years, two black dwarfs might drift close enough to interact significantly. Might, in extraordinarily rare cases, actually collide. A collision between two black dwarfs would be, by the standards of the Black Dwarf Era, a spectacular event. A sudden, violent release of energy in a universe that has grown otherwise utterly silent. A brief, brilliant flash of light and heat in a cosmos that has not seen such things for longer than it saw them when they were common. But these events are vanishingly rare. Separated by timescales so enormous that they represent the exception, not the character, of the era. For every such event, there are vast stretches of uninterrupted quiet. Trillions of years of nothing much happening at all, at any human or even cosmic scale of attention. The universe has become, primarily, a place of deep and almost unbroken stillness. What does it feel like to try to imagine being in this universe? I find it useful to reach for comparisons, even imperfect ones. Think of the quietest place you have ever been. Perhaps somewhere in nature, far from any city or road, on a still night with no wind. Or perhaps somewhere more enclosed, a library after hours, or an empty building in the early morning. A place where the sounds that usually fill your life have receded, and what remains is something you might call quiet, though it is never truly silent. There is always some small sound, if you listen carefully enough. The creak of a building settling, the distant call of an animal, the sound of your own breathing. The universe of the Black Dwarf Era is like that. Like a place that has fallen so deeply quiet that the absence of sound has become its own kind of presence. Where the usual business of things, of stars being born and dying, of galaxies blazing and colliding, of energy flowing and transforming in the grand, ongoing story of a living cosmos, has ceased. Not with violence, not with any drama, just with the gradual, inevitable running down of the processes that sustained all that activity. And in the quiet, a different quality of experience becomes possible. Not worse, not necessarily diminished, just different. The kind of quality that only becomes accessible when the noise falls away. In that universe, in the dark and the cold and the stillness, the black dwarfs drift. Patient, ancient, crystalline, invisible. Each one carrying within its structure the compressed history of a star that once burned, the memory of a solar system that once formed around it, the possibility, however remote, that worlds once orbited it, that life once arose on those worlds, that minds once looked up at the sky and wondered. All of that locked in crystal. Preserved not in any way that could be read or recovered, but preserved in the sense that the matter is still there. The atoms are still the same atoms. The carbon that was once in the core of a star may once have been in the ocean of a living world, in the body of a living thing, in the breath of something that wondered at the universe. Now it drifts in the dark. A black dwarf, cold and invisible and enduring. There is something I want to say about this universe, and I want to say it carefully, because I think it matters. It is easy, when confronted with the image of a dark, cold, silent cosmos, emptied of stars and warmth and light, to feel something like grief, or at least something adjacent to grief. A sadness for what has been lost, a mourning for the light that used to fill the universe, for the stars that burned and the worlds they warmed, and all the extraordinary complexity that flourished in the warmth of stellar fire. And I don't want to dismiss that feeling. It is a real response to a real thing. The universe of the Black Dwarf Era is, by almost any measure, less eventful than the universe we inhabit. Less luminous, less energetic, less full of the kind of activity that we, as beings of warmth and light, tend to equate with aliveness. But I would gently suggest another way of holding it. The universe of the Black Dwarf Era is not a ruined universe. It is not a failed universe. It is not a universe that has lost some battle or fallen short of some ideal. It is simply a universe that has grown old. And there is a different kind of beauty available to things that have grown old. A settled beauty, a patient beauty, the beauty of something that has been through everything and arrived on the other side not diminished but stilled. The black dwarfs drifting through that dark cosmos are not failures. They are the final form of stars. They are what stars become when they have done everything that stars do and have nothing left to burn. They are, in their cold and crystalline permanence, among the most enduring objects the universe produces. Long after the neutron stars have decayed, long after the black holes themselves have eventually, through a process we'll touch on later, evaporated, the black dwarfs may still be there. Patient, dark, cold, still there. And the universe around them, that vast, dark, almost silent cosmos, is still, even in its quietude, a place of extraordinary scale. The distances are still there. The space is still vast, vaster, in fact, than it is now, because the universe has been expanding for all of these trillions upon trillions of years, and the space between objects has grown accordingly. The black dwarfs that were once clustered in galaxies are now, after all the gravitational relaxation and the slow dispersal of galactic remnants, spread across distances so enormous that the light travel time between them, even at the speed of light, would be measured in numbers that dwarf anything we've yet discussed. A universe of extraordinary size. Almost empty. Almost dark. Almost silent. Almost. Because here and there, separated by vast distances, and even vaster stretches of time, things are still happening. Rare things. Quiet things. Things that, in the context of the universe we currently inhabit, would seem impossibly slow. But things nonetheless. The story is not entirely finished. The universe has a few more chapters yet. Strange chapters, slow chapters, chapters that unfold on timescales that make the cooling of a white dwarf look brisk. Chapters about the decay of matter itself. About the slow evaporation of black holes. About what might be the last events in the entire history of the cosmos. We will get to them. But for now, for this moment, in this quiet segment of our journey, let's just be here. In the dark. In the vast, cold, patient dark of a universe that has grown very old. Let the scale of it settle around you like something soft. Not threatening. Not lonely, exactly, but spacious. The kind of spacious that only the very old and the very still can offer. The kind of quiet that has earned itself through an almost incomprehensible passage of time. The black dwarfs are out there. Drifting. Invisible. Enduring. And the universe, for all its darkness, holds them gently. As it holds everything. As it has always held everything. In the dark, and the cold, and the patient, unhurried passage of time. We need to talk about the rules. Not social rules. Not the rules of any human institution, or tradition, or agreement. The rules underneath all of that. The rules that govern not just how people behave, or how societies organize themselves, or how economies function, but how matter behaves. How energy moves. How space and time relate to each other. How the most fundamental constituents of reality interact, at every scale, in every corner of the universe, without exception and without pause. The laws of physics. We tend to think of these as fixed things, permanent things. We don't generally worry, when we drop a glass, that gravity might not be operating today. We don't wonder, when we switch on a light, whether the electromagnetic force has decided to take a break. The laws of physics are, in our experience, absolutely reliable, absolutely consistent. The same in Auckland as in Antarctica. The same on Earth as in a galaxy 10 billion light-years away. The same today as they were 1 billion years ago, and the same as they will be 1 billion years from now. And that is true. The laws themselves do not change. But here is something subtle and important and genuinely fascinating. The laws of physics don't change. But which laws are dominant, which physical effects are the most significant, the most visible, the most consequential in any given situation that shifts? That depends enormously on the conditions. On the temperature, the density, the timescale, the scale of the objects involved. And in the conditions of the Black Dwarf Era, in the extraordinary cold, the extraordinary density, the extraordinary timescales, we have been exploring the physical effects that dominate are not the ones that dominate in our universe today. The rules feel different here. Not because they have changed, but because the universe has moved into a regime where different rules take center stage. Where effects that are completely negligible in our current, warm, energetic cosmos become the primary drivers of what little still happens. Where the physics of the very cold, the very dense, and the very slow becomes the only physics that matters. Tonight, we're going to step into that regime. And it is strange. Beautifully, quietly, profoundly strange. Let's begin with the matter inside the black dwarf itself. We've described the black dwarf's interior as crystallized, a dense, ordered lattice of carbon and oxygen ions, locked into place by the extraordinary pressures within the object. But to understand the deeper physics of what is happening inside a black dwarf, we need to go further than that. We need to look at what is happening not just to the ions, but to the electrons. Because inside a white dwarf, and inside a black dwarf, which is simply a white dwarf that has fully cooled, the electrons are doing something very unusual. Something that has no real parallel in our everyday experience. And that requires a detour into one of the strangest and most counterintuitive corners of physics. That corner is quantum mechanics. Quantum mechanics is the branch of physics that governs the behavior of matter and energy at very small scales. At the scale of atoms and electrons and photons, the fundamental building blocks of everything. And at those scales, the universe behaves in ways that our intuitions, built from a lifetime of experiencing the large-scale world, simply are not equipped to handle. One of the most profound principles of quantum mechanics is something called the Pauli exclusion principle. It was formulated by the Austrian physicist Wolfgang Pauli in the 1920s, and it states, in simple terms, that no two electrons can occupy exactly the same quantum state at the same time. No two electrons in the same system can have exactly the same combination of properties simultaneously. In ordinary matter, in the atoms and molecules of your body, of the chair you might be sitting on, of the air moving in and out of your lungs, this principle operates but doesn't dominate. The electrons in atoms are arranged according to it, which is why atoms have the structure they do, why chemistry works the way it works, why different elements have different properties. But at everyday densities, the electrons have plenty of room to spread out, plenty of available quantum states to occupy, and the Pauli exclusion principle acts quietly in the background without producing anything particularly dramatic. Inside a white dwarf, the situation is completely different. When a dying star's core collapses into a white dwarf, the density increases to something far beyond what ordinary atomic matter experiences. The electrons, which in a normal atom are spread across a large volume relative to the nucleus at the center, are now squeezed into a space so small, and there are so many of them, that all the easily available quantum states are full. Occupied. Every electron is pressed so close to every other electron, and the available space so confined, that the Pauli exclusion principle becomes not a background rule, but the dominant physical reality. And here is the remarkable consequence. When all the available quantum states are filled, and the electrons have nowhere else to go, they resist further compression with an enormous force. Not a force generated by heat, or by any kind of energy in the conventional sense, but a force generated purely by quantum mechanical principle. A resistance born not from temperature, but from the fundamental rules governing what electrons are allowed to do. This is called electron degeneracy pressure, and it is what holds a white dwarf and a black dwarf up. In a living star, what prevents gravitational collapse is the outward pressure of fusion energy. We've talked about this, the balance between gravity pulling inward and fusion pushing outward. But in a white dwarf, there is no fusion. And yet the white dwarf doesn't collapse. Gravity is pressing inward, as it always does, with the weight of nearly a solar mass of material. And the white dwarf holds its shape anyway. It holds its shape because of quantum mechanics. The degenerate electrons, packed into every available quantum state, simply refuse, at a fundamental physical level, to be squeezed any further. They push back, not because they are hot, not because they are moving particularly fast in any conventional thermal sense, but because the laws of quantum mechanics forbid them from occupying less space than they currently do. This is degenerate matter. Matter in which the normal relationship between pressure and temperature has been broken. In ordinary matter, if you cool something down, it contracts, loses thermal pressure, becomes denser, settles into a lower energy state. But degenerate matter doesn't behave this way. You can cool a white dwarf from 100,000 degrees to just a fraction of a degree above absolute zero, and its size barely changes. The electron degeneracy pressure that supports it is almost entirely independent of temperature. The cold dwarf is nearly the same size as the hot dwarf. This is why a black dwarf, for all its extraordinary coldness, is not crushed by its own gravity. The quantum mechanical resistance of its degenerate electrons keeps it intact, keeps it stable, preserves its structure through the trillions upon trillions of years of cooling, through the crystallization of its interior, through the final Debye cooling phase, and beyond, into the cold and silent ages beyond. Quantum mechanics, quite literally, holds the black dwarf together. Now, let's go deeper, because there is something else happening inside a black dwarf, something even slower, even stranger, even more remote from anything our everyday experience prepares us for. Something that, in the current universe, is so negligible as to be essentially unmeasurable, but that, given enough time, becomes one of the defining physical processes of the deep future. It involves the stability of the matter itself. We tend to assume, without thinking much about it, that the atoms in ordinary matter are stable, that a carbon atom, left alone, will remain a carbon atom. That an oxygen atom will remain an oxygen atom. That the protons and neutrons in the nuclei of these atoms are simply there, permanent and unchanging, for as long as you care to wait. And in the time frame of human experience, even in the time frame of the current age of the universe, this assumption is entirely justified. Protons, in particular, are extraordinarily stable. The experimental lower bound on the proton lifetime, the minimum lifetime that experiments have been able to establish, is extraordinarily long. Far longer than the current age of the universe. But extraordinarily long is not the same as infinite. Many extensions of our best current theories of physics theories that go beyond the standard model, attempting to unify the fundamental forces of nature into a single framework, predict that protons are not, in fact, perfectly stable. That given sufficient time, a proton will eventually decay, transform into other particles, shed its identity as a proton, and become something else, a pion, perhaps, and a positron. Particles that will themselves quickly decay or annihilate, releasing a tiny pulse of energy in the process. The predicted timescale for proton decay, if it happens at all, is somewhere around 10 to the power of 33 to 10 to the power of 40 years. Those numbers are so far beyond anything we've discussed tonight that they require a moment of pause. 10 to the power of 33 years. That is a 1 followed by 33 zeros. Compare that to the current age of the universe, 10 to the power of 10 years. The ratio between these two numbers is so large that even the ratio is difficult to process. Proton decay, if it occurs, operates on timescales that make the cooling of a black dwarf look immediate. Make the entire Black Dwarf Era look like a brief prelude. But given enough time, and in the deep future of the universe, there is time, and more than time, even protons decay. And if protons decay, then the black dwarfs, those patient, crystalline, enduring spheres of compressed carbon and oxygen, will not last forever after all. They will, over almost unimaginably long timescales, slowly dissolve. Atom by atom, proton by patient proton, transforming from dense stellar remnants into diffuse clouds of lighter particles, releasing their stored mass as faint radiation over periods of time so vast that the entire Black Dwarf Era itself, already spanning timescales that make the current age of the universe look like an instant, would be merely the opening act. There is something I find extraordinary about this. We have been talking about the black dwarf as a symbol of endurance, of patience, of the quiet persistence of matter in the face of a universe that has grown cold and dark and still. And that endurance is real, it is extraordinary and genuine, and worth marveling at. But physics, it turns out, has one more card to play. Even the endurance of matter itself is, on the longest timescales, provisional. Even the atoms inside a black dwarf are, if our best theoretical extensions are correct, quietly counting down to their own eventual transformation. Not quickly. Not on any timescale that would be perceptible even against the background of the Black Dwarf Era. But eventually, in the deep, deep future, long after even black dwarfs have had their extraordinarily long moment in the cosmos. And yet there is something peaceful in this, rather than distressing at least, I find it so. Because physics is not a story about permanence. It never has been. It is a story about transformation. About matter and energy taking one form, and then another changing, always, but not disappearing. The atoms in a black dwarf were once gas in an interstellar cloud. Before that, they were forged in the cores of even earlier stars. Before that, they were hydrogen and helium produced in the first minutes after the Big Bang. And if those atoms eventually decay, if the protons within them eventually transform into lighter particles, if the black dwarf slowly dissolves over unimaginable ages, then those particles will go on to become something else. What exactly? We don't fully know. We are, in some of these regimes, at the edges of our current understanding, speculating carefully, guided by mathematics and physical principle, but speculating nonetheless. And that is fine. That is, in fact, rather wonderful, because it means the universe still has secrets. Even when we look as far as physics currently allows, into the deepest, coldest, strangest future we can model, there are still things we don't entirely know. Still questions that haven't been answered. Still, in some sense, more story to be told. Let's return, for a moment, to the interior of the Black Dwarf. To that cold, crystalline, quantum-mechanical object drifting in the dark. We have established that it is held together by electron degeneracy pressure. That quantum mechanics is the dominant physical principle governing its structure. That the matter inside it is, on extraordinarily long timescales, subject to processes, like proton decay, that have no significance whatsoever in the universe we currently inhabit. But there are other quantum processes, too. Subtler ones. Things that happen at the boundaries of our understanding, in the cold and the dark and the quantum deep. One of them is quantum tunneling. Quantum tunneling is one of those phenomena that sounds, when you first encounter it, completely impossible. And by the standards of everyday intuition, it is. Tunneling refers to the ability of quantum particles, electrons, protons, atoms themselves, to pass through barriers that classical physics says they cannot cross. Not to go over the barrier, or around it, but through it. To appear on the other side of an energy barrier, without having had the energy to surmount it. This happens all the time in the current universe, at small scales. It is how fusion occurs in the cores of stars. Protons tunnel through the electromagnetic repulsion that would otherwise prevent them from getting close enough to fuse. Without quantum tunneling, stars could not burn. Our sun could not shine. But tunneling also occurs in other contexts. And in the cold, dense interior of a black dwarf, over the extraordinarily long timescales of the deep future, tunneling may drive processes that would be laughably improbable in any shorter time frame. One such process is the rearrangement of atomic nuclei. In theory, given enough time, quantum tunneling could allow the nuclei within a black dwarf, currently locked in a crystalline lattice of carbon and oxygen, to slowly rearrange themselves into more energetically stable configurations. The most stable nucleus, the one with the lowest energy per nucleon, is iron. And so there is a theoretical process sometimes called quantum tunneling nucleosynthesis, or simply the long-term nuclear rearrangement of black dwarfs, by which, over extraordinarily long timescales, the carbon and oxygen inside a black dwarf might slowly tunnel their way toward becoming iron. The timescale for this? Somewhere around 10 to the power of 1,500 years. A 1 followed by 1,500 zeros. We will not attempt an analogy for this number. There isn't one that works. It is simply a number so large that it sits beyond the reach of any comparison, beyond the capacity of any image or metaphor to illuminate. It is a number that exists in mathematics and in careful physical reasoning, and that is where it is most comfortable. We can gesture toward it. We can acknowledge its existence. And then we can let it be as large as it is, and not trouble ourselves further with trying to grasp it. Just know that even in the apparent permanence of a black dwarf, even in that cold, crystalline, ancient sphere, there are processes occurring. Slowly, on timescales that dwarf all other timescales we have considered. But occurring. The universe, even in its oldest and quietest age, does not entirely stop. What does all of this mean, taken together? It means that the physics of the Black Dwarf Era is genuinely different, in character, from the physics of the universe we inhabit. In our universe warm, energetic, filled with stars and radiation, and the constant cycling of matter, through stellar processes the dominant physics is thermal. Chemical. Nuclear, in the stellar sense. Things happen because they are hot enough to happen. Because there is enough energy moving around to drive reactions, to overcome barriers, to sustain the constant transformation of matter and energy that we call, loosely, the activity of the universe. In the Black Dwarf Era, the heat is gone. The energy is gone, or so nearly gone as to make no practical difference. The thermal physics that governs almost everything in our current experience has become irrelevant. What remains is quantum physics. Pure, cold, unhurried quantum physics, operating on timescales so vast that the processes it drives are essentially invisible against any background shorter than the age of the universe itself. Electron degeneracy pressure holding matter together. Proton decay slowly dissolving it. Quantum tunneling rearranging it, grain by patient grain, over timescales that make all previous timescales look brief. The universe has not stopped following its laws. It has simply moved into a different part of those laws. A part we rarely see, rarely measure, rarely need to think about in the warm and energetic conditions of the present age. A cold part, a quantum part, a part that operates in silence and darkness, on timescales that require a particular kind of patience to contemplate. I want to close this segment with something that I think captures the quality of this physics in a way that pure description sometimes misses. There is a concept in music called a drone. A single sustained note, held beneath the melody, a deep, continuous sound that doesn't change, that doesn't resolve into something else, that simply persists. In certain traditions of music, in certain meditative practices, this drone is considered not empty or boring but full. Rich. A foundation that gives everything else meaning precisely because it is steady and unbroken. The quantum physics of the Black Dwarf Era is something like that drone. In our universe, warm, bright, energetic, the melody is loud and complex and constantly changing. Stars being born and dying. Galaxies colliding. Supernovae blazing. The constant, rapid transformation of matter and energy in every direction. The quantum effects are there, underneath it all, but they are drowned out by the melody. Inaudible. In the Black Dwarf Era, the melody has ended. The stars are gone. The energy is spent. The brightness and warmth and activity of the Stelliferous Age have faded into memory. What remains is the drone. Quantum mechanics, patient and deep and cold. Electron degeneracy, holding matter in shape. Proton decay slowly, almost imperceptibly, transforming it. Tunneling, rearranging it, one quantum event at a time, across timescales that dissolve all ordinary meaning from the word slow. The rules are the same rules, but they feel different here. They feel like the bottom of something, like the floor of the universe, finally audible now that everything louder has gone quiet. And there is, in that quiet, a strange and genuine beauty, if you know how to listen for it. The Black Dwarf Era, Segment 9. What happens next? Two possible futures. Here is something that doesn't happen very often in science. A genuine fork in the road. Not a matter of fine-tuning. Not a debate about whether a number is slightly larger or slightly smaller than we currently measure it to be. But a real, fundamental branching of possibility. Two futures, genuinely distinct from each other, each internally consistent, each supported by serious physics, each leading to a completely different fate for the matter sitting inside a black dwarf. Two roads. And we don't yet know which one the universe is actually taking. We have sent experiments deep underground. Enormous detectors filled with thousands of tons of water or liquid, shielded from cosmic radiation by mountains of rock above them, specifically to try to answer this question. To try to catch a proton in the act of decaying, to measure the lifetime of the most abundant particle in ordinary matter, to determine once and for all which of these two roads the universe has chosen. So far, the protons have not cooperated. Not a single confirmed proton decay has ever been observed. Which tells us something, that if protons do decay, they are extraordinarily patient about it, more patient than our experiments have yet had time to detect. But it does not tell us they are stable. The absence of an observed event is not the same as evidence that the event never occurs. It may simply mean we haven't waited long enough, haven't built a large enough detector, haven't yet found the right signature to look for. And so the question remains open. And tonight, in the spirit of that openness, in the spirit of sitting comfortably with genuine uncertainty, which is one of the most intellectually honest things a person can do, we are going to follow both roads. We are going to walk a little way down each path, and see where it leads, and let the two futures exist side by side in our imagination, the way they exist side by side in our physics. Because both are extraordinary. Both are, in their own distinct way, quietly astonishing. Let's take the first road. The road where protons decay. If protons are not perfectly stable, if the extensions to our current physics that predict their eventual decay turn out to be correct, then the fate of a black dwarf is, in the longest view, a slow dissolution. A gradual, patient coming apart, piece by piece, particle by particle, over timescales that make everything we have discussed so far look brief. Remember what a proton is. A proton is one of the two types of particle, along with neutrons, that make up atomic nuclei. Every atom in the universe, other than the simplest hydrogen atom, contains multiple protons in its nucleus, bound together with neutrons by the strong nuclear force. The protons give the atom its identity. The number of protons in a nucleus determines what element it is. 1 proton, hydrogen. 6 protons, carbon. 8 protons, oxygen. Remove or transform the protons, and you change or destroy the atom. If a proton decays, it transforms. Most theoretical models of proton decay suggest it would produce a positron, the antimatter counterpart of an electron, and a neutral pion, which is itself an unstable particle that almost immediately decays further into photons. Gamma rays, a tiny pulse of energy, released into the surrounding space. And then that proton is simply gone. No longer a proton. No longer a constituent of any nucleus. The atom it belonged to has been changed, destabilized, transformed into something else, or simply come apart. Now, in a black dwarf, this process would be extraordinarily slow. A single proton decay event in a given black dwarf might occur, perhaps once every 100 million years or so. The exact rate depending on the specific proton lifetime, which we don't yet know. Each event releases a tiny pulse of energy, a whisper of gamma radiation into the surrounding dark, and then silence again for another 100 million years before the next. Over the full timescale of proton decay, that's staggering 10 to the power of 33 to 40 years. Every single proton in the black dwarf would eventually undergo this transformation. Every carbon nucleus, every oxygen nucleus, every atom in that ancient crystalline sphere, slowly, one by one, losing protons until the nuclei come apart, until the atoms cease to exist in any recognizable form. What is left when all the protons have decayed? The electrons, which are not made of protons, and which most models of proton decay do not predict will decay on any similar timescale, would remain. Adrift, freed from the nuclei they once surrounded. Along with whatever particles were produced in the proton decay events themselves, positrons, photons, neutrinos, most of which would have long since departed or annihilated. The black dwarf, over these extraordinary timescales, would essentially evaporate. Not dramatically, not all at once, but grain by grain, proton by proton, in the quietest and most drawn-out dissolution imaginable. The crystalline structure, that ancient lattice of carbon and oxygen ions that we spent so much time marveling at, would slowly lose coherence. The ions would lose the protons that define them. The lattice would come apart, and the mass of the black dwarf, that stellar mass compressed into a planetary volume, preserved through trillions of years of patient cooling, would disperse. Not into nothing. Energy is always conserved, and mass is a form of energy. The mass of those decayed protons would become photons, neutrinos, positrons, particles moving outward into the surrounding space at nearly the speed of light. The black dwarf would, over a timescale of 10 to the power of 33 to 40 years, slowly convert itself into light. Not gloriously, not in any way that would be visible or dramatic on any human or even cosmic timescale. Just quietly, one proton at a time, releasing its stored mass as tiny pulses of radiation into a universe that by then would be extraordinarily cold and dark and empty. A last faint glow, spread over almost incomprehensible time. The final warmth of something that was once a star. There is something almost unbearably poignant about that image, if you let yourself feel it. A star that spent billions of years burning magnificently, warming planets, driving photosynthesis, making life possible, collapsing into a white dwarf, cooling over trillions of years into a black dwarf, and then over timescales 1 trillion times longer still, slowly dissolving, giving its last stored energy back to the universe, one proton at a time, one tiny gamma-ray photon at a time. Not wasted. Never wasted. The energy doesn't disappear. It propagates outward, becomes part of the background radiation of the universe, joins the almost infinitely thin and cold sea of photons and neutrinos that by then constitutes the energy content of the cosmos. The star's energy dispersed. Its matter transformed. Its history preserved in nothing more substantial than the faint, ancient photons moving away from where it once was. And then, after all of that, the black dwarf is gone. Or rather, what was a black dwarf is now something else. Something diffuse and cold and scattered. The matter has changed form, as matter always does. But the story has moved on. The chapter has ended. If protons decay, that is the ending. Now let's walk back to the fork in the road, and take the other path. The road where protons are stable. If protons do not decay, if they are truly, genuinely stable, as our most direct experimental evidence currently suggests, then the black dwarf does not dissolve in the way we just described. It does not slowly convert its matter into radiation. It persists, in the sense that its protons persist, in the sense that its atomic nuclei remain intact, for timescales that might, depending on what else is happening, approach something like genuine permanence. But the physics does not stand entirely still, even in this scenario, because there is another process at work inside the black dwarf. A process that operates, like so much of the physics in this era, on timescales so vast that we never see it in the current universe. But that is real, and that is significant, and that leads to a fate for the stable black dwarf that is, in its own way, just as extraordinary as the proton decay scenario. That process is called pycnonuclear fusion. The word pycnonuclear comes from the Greek word for dense, pyknos, dense nuclear fusion. Fusion that occurs not because of heat, but because of density. In ordinary stellar fusion, the kind that powers stars like our Sun, nuclei are brought close enough to fuse because they are moving extremely fast. The temperature in a stellar core is so high, the thermal motion of the particles so violent, that nuclei can overcome their mutual electromagnetic repulsion. The fact that two positively charged things strongly resist being pushed together, and get close enough for the strong nuclear force to grab them and fuse them into a new nucleus. Heat, in other words, is what makes ordinary fusion go. High temperature means high particle velocity, means sufficient collision energy to overcome the repulsion barrier. In a black dwarf, there is no heat. The temperature is effectively zero. The nuclei are locked in a crystal lattice, not moving freely at all. Ordinary thermal fusion is completely impossible. But in a dense enough environment, and a black dwarf is extraordinarily dense, something else can happen. The nuclei, even though they are locked in their lattice positions, even though they have no thermal energy to throw at the repulsion barrier, are close enough to each other, and the quantum mechanical phenomenon of tunneling is real enough, that very occasionally, a nucleus can tunnel through the electromagnetic barrier and fuse with its neighbor. Without the heat, without the velocity, just by virtue of being extraordinarily close, and quantum mechanics being what it is. This is pycnonuclear fusion. And in a black dwarf, it is occurring right now, in a theoretical sense at least, at an almost imperceptibly slow rate. The conditions are right for it in principle. The density is sufficient. The nuclei are close enough. Quantum tunneling is, as we've established, a real physical phenomenon. It is just very, very, very slow. How slow? The rate of pycnonuclear fusion in a black dwarf depends sensitively on the density and the composition of the material. For a black dwarf made primarily of carbon and oxygen, as most will be, the rate is so low that a meaningful amount of fusion happening in any human observable time would be inconceivable. We are talking about events that occur in any given small region of the black dwarf, perhaps once in an extraordinary span of time, perhaps once in a span that is itself already comparable to the timescales we have been discussing throughout this entire journey. But, and this is the crucial thing, it does occur. Slowly, inexorably, grain by quantum grain, the nuclei inside the black dwarf are fusing. Carbon fusing with carbon. Oxygen fusing with oxygen and carbon. Heavier elements forming, over time, from lighter ones. And the direction of this process is, in terms of nuclear physics, entirely predictable. Because there is a most stable nucleus, an endpoint toward which nuclear fusion, given time and the right conditions, always tends to move. We mentioned it briefly in our last segment. That endpoint is iron. Iron 56, to be precise, a nucleus containing 26 protons and 30 neutrons, which sits at the absolute minimum of nuclear binding energy per nucleon. The most energetically favorable nucleus that exists. The nucleus toward which both fusion and fission, in their different ways, tend to move matter over time. Stars know this. A massive star, burning through its sequence of nuclear fuels, builds progressively heavier elements in its core. Hydrogen to helium, helium to carbon, carbon to neon, neon to oxygen, oxygen to silicon, silicon to iron. And when the iron core grows large enough, the star can go no further. Iron fusion does not release energy, it requires it. And the star collapses. But in a black dwarf, the process is not driven by heat. It is driven by quantum tunneling and density alone, operating on timescales that make stellar evolution look instantaneous. And given sufficient time, truly sufficient time, the kind of time we have been talking about throughout this entire journey, the pycnonuclear fusion occurring inside a stable black dwarf will gradually convert its carbon and oxygen into heavier and heavier elements, moving, step by quantum step, toward iron. The timescale for a black dwarf to significantly rearrange its composition through pycnonuclear fusion is, as we touched on last time, somewhere in the region of 10 to the power of 1,500 years. We agreed, last segment, not to attempt an analogy for that number. I will keep that agreement. But the physical reality it represents is genuinely remarkable. A black dwarf that is stable against proton decay will, over this extraordinary timescale, slowly transform. The crystal lattice that we marveled at, that ancient, ordered structure of carbon and oxygen ions, locked in place by the extraordinary density of the object, will, grain by patient grain, be rearranged. The lighter nuclei will fuse, through quantum tunneling, into heavier ones. The composition of the black dwarf will shift. And eventually, given time enough, and if protons are stable, there is time enough, the black dwarf will no longer be primarily carbon and oxygen. It will have become, in its core and gradually throughout its volume, primarily iron. An iron black dwarf. A sphere the size of a planet, the mass of a star, made almost entirely of iron, 56 nuclei locked in a dense crystal lattice, drifting invisibly through an almost unimaginably ancient and cold universe. The most stable form that ordinary matter, left to its own devices for long enough, can reach. The universe's equivalent of a final resting state. At least for matter. Let's step back from both roads for a moment, and look at what they have in common. Because for all their differences, one ending in slow dissolution, one ending in a cold iron sphere, both futures share something that I find genuinely moving. In both cases, the black dwarf is the last inheritor of the star's legacy. In both cases, the matter that was once a star, that was born in a nebula, that sustained fusion for billions of years, that shed its outer layers in a beautiful planetary nebula, that cooled for trillions of years, through every stage of the white dwarf's long farewell. That matter persists, in the black dwarf, long after everything else from that era has gone. The photons that the star emitted during its lifetime are long gone, absorbed, scattered, redshifted into the background radiation of an expanding universe. The planetary nebula dispersed and faded billions of years before the black dwarf formed. Even the other black dwarfs from the same galactic neighborhood may have been flung outward into intergalactic space by gravitational interactions. But the matter itself, the carbon, the oxygen, the iron into which they may eventually transform, stays. Locked in the black dwarf. Preserved in the extraordinary density of degenerate matter. Going wherever the black dwarf goes. Drifting slowly through the dark, subject to the occasional gravitational nudge, but fundamentally persisting. Until finally, either through proton decay or through pycnonuclear transformation, it becomes something else. Not nothing. Never nothing. Just something else. And here is, perhaps, the deepest thought I can offer as we stand at this fork in the road. We don't know which path the universe has chosen. We are standing here, tonight, with our physics and our experiments and our careful mathematics, and we genuinely, truly do not know whether protons decay. We have looked as hard as we can, with the best instruments we have been able to build, and the answer has not yet come. It may come, one day. Some future experiment may finally catch a proton in the act of decay, and one of these two futures will be confirmed over the other. Or it may be that protons are genuinely stable, and no experiment will ever observe their decay, and our confidence in their stability will simply grow and grow without ever becoming certainty. The universe keeps its own counsel on this, and I find something genuinely peaceful in that. In the idea that the deepest futures, the fates of the last cold remnants of the last dead stars, in a universe so old and dark and quiet that the very concept of observation has become almost meaningless, are still, from where we sit tonight, genuinely open. Not decided. Not foreclosed. Two futures, both possible. Both extraordinary. Both arriving, by different roads, at the same fundamental truth that matter transforms and energy persists, and the universe, for all its aging and quieting and darkening, never quite settles into absolute stillness. There is always something happening, even in the dark, even after the last star has gone out, and the last white dwarf has cooled, and the first black dwarfs have begun their own extraordinarily long vigil in the cold. Something is always, somewhere, slowly happening. Proton by proton, nucleus by tunneling nucleus. In the patient, quantum dark, the electron degeneracy pressure, which has held the object together through trillions upon trillions of years of cooling and crystallization and quantum rearrangement, is no longer quite sufficient to hold back the gravity of a solar mass or more of matter, and the black dwarf begins to collapse. Now, what happens when something close to the Chandrasekhar limit collapses? In our current universe, we have a template for this. When a white dwarf in a binary star system accretes material from its companion, gradually gaining mass until it approaches the Chandrasekhar limit, the result is a Type Ia supernova, a catastrophic thermonuclear explosion in which the entire white dwarf is consumed in a runaway fusion reaction, releasing an amount of energy comparable to what our Sun will emit over its entire 10 billion year life, released in a matter of seconds. Type Ia supernovae are among the brightest events in the universe. They outshine entire galaxies for weeks. They are so consistently luminous that astronomers use them as standard candles, objects of known brightness that can be used to measure cosmic distances. The discovery that the universe's expansion is accelerating was made, in large part, by observing Type Ia supernovae. They are spectacular. They are violent. They are among the most energetic things that happen in the cosmos. And something like them, something hauntingly reminiscent of them, though different in crucial ways, may occur in the Black Dwarf Era. When a massive black dwarf crosses the threshold imposed by its own compositional evolution, when its electron degeneracy pressure finally fails and gravity begins to win, the object begins to collapse. The density in the core increases rapidly, and as the density spikes, something extraordinary happens. The pycnonuclear fusion rate, which had been occurring at an almost imperceptibly slow pace for an almost incomprehensible length of time, suddenly, dramatically accelerates. Because pycnonuclear fusion rates depend exquisitely on density. They increase enormously as density increases. And as the black dwarf collapses, and its core density spikes, the fusion rate goes from glacially slow to almost instantaneous on these timescales. A runaway process. A cascade. The nuclei in the core begin fusing rapidly, not through thermal motion, but through the suddenly extreme density, through the compression of collapse. Energy is released. More collapse occurs. More fusion. More energy. A feedback loop, violent and sudden by the standards of anything that has happened in this quiet, ancient universe. What results is something that has been called, by the physicists who have explored these theoretical futures, a black dwarf supernova. Not identical to the Type Ia supernovae of our current era. The conditions are different. The mechanism is driven by density and quantum tunneling rather than by accreted mass, and the composition of the object is different from a freshly cooled white dwarf, but similar in its essential character. A sudden, violent release of energy from an object that had been cold and dark and silent for a span of time that makes the entire history of the universe look like a brief prologue. A flash of light in a universe that has been dark for longer than the mind can hold. Sit with that image for a moment. The universe of the Black Dwarf Era. Dark, cold, quiet beyond all comparison to anything in our current experience. The remnant structures of what were once galaxies, drifting slowly through the expanding void, populated by invisible black dwarfs and cold neutron stars, and the patient, enormous gravity wells of black holes. No stars, no nebulae, no new light being generated anywhere. Just the occasional faint pulse of a proton decaying, if they decay, or the even more occasional quantum tunneling event rearranging a pair of nuclei in the lattice of an ancient crystalline sphere. And then, in some remote region of the universe, around some specific black dwarf, one of the most massive of its kind, one that has been slowly evolving through pycnonuclear fusion for a span of time that dwarfs all other timescales in this story, the threshold is crossed. The support fails. The collapse begins. The density spikes. The fusion cascades. And a supernova blazes. A single, brilliant point of light in an otherwise completely dark universe. An explosion releasing more energy in its brief duration than that particular object had emitted, in total, in all the trillions upon trillions of years of its white dwarf cooling phase. Light and heat, and a shockwave expanding outward into dark space that has not felt a shockwave in longer than stars have been gone. There may be no one to see it. Almost certainly, there is no one to see it. By the timescales we are discussing, 10 to the power of 32 years, 10 to the power of 60 years, and beyond, the question of whether any consciousness exists anywhere in the universe to observe anything is one that physics cannot answer, and that belongs to realms of speculation well beyond our journey tonight. But the event occurs regardless. The light expands outward regardless. The physics happens, as physics always happens, indifferent to observation, indifferent to audience, following its own rules in its own time, whether or not anyone is there to notice. A black dwarf supernova, in a universe that has been dark for longer than it was ever light. And then the light fades, as it always does. The shockwave expands and cools. The debris disperses into the surrounding space. Iron and other heavy elements, the products of that final cascading fusion, joining the cold sparse material of an ancient universe. And the universe is dark again. Until the next one. How often do these events occur? How many massive black dwarfs will eventually cross the threshold and produce these extraordinary, solitary explosions? The numbers are difficult to estimate with precision because they depend on the specific distribution of black dwarf masses, which depends on the original distribution of stellar masses, and on the detailed timescales of pycnonuclear fusion in near Chandrasekhar mass objects. But whatever the exact frequency, it is extraordinarily low. We are talking about events separated by timescales that, themselves, compare to the cooling time of a black dwarf the way the cooling time of a black dwarf compares to a human heartbeat. These are not regular occurrences. They are not even rare occurrences, in any sense that the word rare usually implies. They are among the most isolated, most infrequent events in the entire future history of the universe. Each one separated from the previous, one by a stretch of dark, cold, silent waiting that makes every other waiting we have discussed tonight look impatient by comparison. And yet, they happen. Eventually. One by one. Here and there, scattered across a universe so vast and dark and ancient that the distance between consecutive events, measured in both space and time, is almost beyond contemplation. They happen. There are other things happening too, in this era. Other slow processes playing out on extraordinary timescales. Other consequences of physics operating patiently in the dark. Black holes, for instance, are not exempt from time. In our current universe, black holes seem permanent, regions of space-time so severely curved that nothing escapes, not even light, accumulating mass from anything that crosses their event horizons, growing slowly larger and more massive. They seem, from our current vantage point, like the most enduring things in the cosmos. But Stephen Hawking showed, through a beautiful theoretical argument combining quantum mechanics and general relativity, that black holes are not perfectly stable. That quantum effects at the event horizon cause them to slowly, almost imperceptibly, radiate energy into the surrounding space. To lose mass, particle by particle, in a process so slow that for the largest black holes it would take an almost incomprehensible span of time to produce any measurable effect. This Hawking radiation, as it is called, causes black holes to very slowly evaporate. The largest black holes, the supermassive ones at the centers of galaxies, will take something in the range of 10 to the power of 80 to 100 years to evaporate completely. Those timescales sit alongside the timescales of the Black Dwarf Era and its aftermath. Enormous, yes, but not entirely dissimilar in character to some of what we have already discussed. And when the last black hole evaporates, when the last of those patient, enormous gravitational singularities finally releases its last Hawking photon into the surrounding dark, the universe will have lost one of the last truly dynamic objects it possessed. What remains after that is even quieter, even more patient, even more still. Let's step back, as we have done before, and look at the sweep of all of this. We began tonight with the image of a universe with no stars. A dark, cold, silent cosmos populated by invisible remnants. We traced the journey of a single star from birth to death, from white dwarf to black dwarf. We marveled at the timescales of cooling. We explored the quantum physics of degenerate matter. We followed the two possible futures of a proton. And now we have arrived at the very edge of what our physics can tell us, at the timescales of black dwarf supernovae and black hole evaporation, and the slow pycnonuclear transformation of matter toward its most stable form. And through all of it, one theme has persisted. Change never fully stops. Not in the Black Dwarf Era. Not in the eras that follow. Not ever, as far as we can tell, not on any timescale that our physics can currently reach. The universe is always doing something. Even if that something is extraordinarily slow, even if it is a single proton decaying in a cold dark sphere over a timescale that makes all of previous cosmic history look like the blink of an eye. Something is always happening. There is something almost stubborn about this. Something that feels, if you'll allow a small piece of anthropomorphism, almost determined. The universe does not appear to have a setting for complete, absolute stillness. It approaches stillness, asymptotically, as mathematicians would say, getting closer and closer to a limit it never quite reaches. Every process runs down, every energy gradient levels out, every source of activity eventually exhausts itself. But before the last one does, there is always, it seems, at least one more thing happening somewhere. The longest waiting game, the deepest patience, the most extraordinary persistence of change in the face of an entropy that wants, above all things, for everything to simply settle. I find myself, at this point in our journey, wanting to say something about waiting itself. Because we have been describing, essentially, a universe that is waiting. Waiting through the cooling of white dwarfs. Waiting through the crystallization of black dwarfs. Waiting through the pycnonuclear rearrangement of nuclei over 10 to the power of 1500 years. Waiting through the occasional black dwarf supernova, and the long dark silence that follows each one. Waiting through the slow evaporation of black holes. Waiting through the decay of protons, if they decay. All of this waiting. And in our human lives, waiting is often the difficult thing. The uncomfortable thing. We are creatures of activity, of purpose, of forward motion. Waiting feels like the absence of living, sometimes. Like time that is being used up rather than used. But out here, in the deep future of the universe, in the timescales of black dwarfs and quantum processes, and the longest games that physics plays, waiting is not the opposite of activity. It is the medium through which activity occurs. The slow processes are not waiting to become fast processes. They are simply operating at their own natural pace, governed by their own physical laws, neither hurried nor delayed. The universe does not experience its waiting as waiting. It is simply being what it is, changing at the rate it changes, doing what the laws of physics, operating in conditions of extraordinary cold and extraordinary density and extraordinary age, determine it to do. And there is something in that, something in the image of a universe simply being what it is, without impatience, without rushing toward any conclusion, without any sense that the slowness is a problem to be solved, that I find genuinely restful to contemplate. We spend so much of our lives trying to move faster, to do more, to compress experience into smaller and smaller parcels of time, to be productive, to be efficient, to not waste a moment. And all of that has its place. It is part of what makes us human, part of what makes consciousness such a remarkable and generative thing. But occasionally, in the quiet hours, in the dark, in those moments between wakefulness and sleep when the urgency of the day has finally receded, it can be a relief to remember that the universe, in its deepest nature, is not in a hurry. It has been at this for 10 to the power of 32 years and more. It will continue for longer still. It is not rushing. Neither, tonight, are we. The black dwarfs are out there, in that deep future dark. Some cooling. Some already fully cold. Some, the most massive ones, slowly, quantumly, patiently evolving toward the moment when their support fails and they blaze, briefly and brilliantly and unobserved, in the longest night there has ever been. And the universe holds all of this. Holds it the way the dark holds everything that happens within it. Without preference, without judgment, without hurry. Just holds it. In the patience of physics. In the quiet of extraordinary time. And somewhere, in all that dark and all that waiting, the story is still going on. Still somehow going on. Come back. Gently now. No rush. But come back from the deep future. From the dark and the cold and the extraordinary timescales we have been inhabiting together. Come back from the black dwarf supernovae blazing alone in an ancient, starless universe. Come back from the quantum tunneling and the proton decay and the pycnonuclear rearrangement of matter across timescales that dissolve all ordinary meaning from the word long. Come back to now, to this moment, to this night, to a universe that is 13.8 billion years old and still, by the standards of everything we have explored, extraordinarily young. A universe still full of stars, still blazing with light in every direction. Still, in the cosmic sense, at the beginning of its story. We have been a long way out tonight, in our imagination. We have stood at extraordinary distances, not in space, but in time, and looked back at the universe we currently inhabit from a vantage point so remote that our entire cosmic age would be invisible to it, a rounding error, a footnote. And now we return. Not because the deep future isn't worth contemplating. Everything we have explored tonight suggests that it is, profoundly so. But because there is something important waiting for us back here, in the present. Something that connects all of that extraordinary distance to the work that real astronomers, at real telescopes, in real observatories around the world, are doing right now. Tonight. In the same darkness that holds all of those future possibilities. Because the Black Dwarf Era is not only a story about the future, it is also, perhaps surprisingly, a story about the past, and about how we know what we know. Let's start with a question that might seem simple, but turns out to be surprisingly deep. How old is the Milky Way? Not the universe. We have a fairly good handle on that, through multiple independent lines of evidence, converging on roughly 13.8 billion years. But our galaxy specifically. The great spiral structure of stars and gas and dust and dark matter that we call home, that the Sun orbits once every 230 million years or so, that contains something in the region of 200 to 400 billion stars. How old is it? This matters for all sorts of reasons. It matters for understanding the history of the universe. When galaxies like ours formed, how they assembled from smaller structures in the early cosmos, how the star formation history of our galaxy relates to the broader story of cosmic evolution. It matters for understanding the history of the elements, when the carbon and oxygen and iron that make up our world were forged, in which generations of stars, over what timescale. It matters in a sense that is hard to fully articulate, but easy to feel, for understanding where we come from. Answering it, though, is not straightforward. You cannot simply look at a galaxy and read its age from its face, the way a geologist can read the age of a rock layer, or a doctor can estimate a patient's age from a medical scan. Galaxies don't come with clear labels. They're stars formed at different times, from different generations of gas, and they exist now in a vast mixed population, where young stars and ancient stars coexist in the same galactic neighborhood, without any obvious visible distinction between them. So how do astronomers approach this problem? One of the most powerful methods involves white dwarfs. White dwarfs, it turns out, are extraordinary natural clocks. We established, earlier in our journey, that white dwarfs cool at a known rate, slowly, following the physics of thermal radiation and crystallization and Debye cooling, according to principles that we understand reasonably well and can model with considerable precision. A white dwarf formed 1 billion years ago will have cooled to a predictable temperature. One formed 5 billion years ago will be cooler still. One formed 10 billion years ago will be cooler again. The relationship between a white dwarf's temperature and its age, from the moment it formed, is something we can calculate. Not perfectly, not without uncertainties, but well enough to be genuinely useful. And this means that if you can measure the temperature of a white dwarf, you can estimate, within reasonable bounds, how long it has been cooling, how old it is, when it formed. This is called white dwarf cosmochronology. A wonderful word, cosmochronology. The measurement of cosmic time. The reading of the universe's clock from the cooling of its dead stars. And it works like this. Within a star cluster, a group of stars that all formed from the same cloud of gas at roughly the same time, you can observe the population of white dwarfs. You can measure their temperatures and luminosities. And you can look for the coolest, dimmest white dwarfs in the cluster, the ones that have been cooling the longest, that formed earliest, that represent the oldest stellar remnants in the group. The temperature of the coolest white dwarfs in a cluster places a lower bound on how long those white dwarfs have been cooling, which in turn places a lower bound on the age of the cluster itself. If the coolest white dwarfs have been cooling for, say, 8 billion years, then the cluster must be at least 8 billion years old. Probably a little older, accounting for the time the progenitor stars spent on the main sequence before becoming white dwarfs. This method has been applied to star clusters throughout our galaxy. To the ancient globular clusters, those dense, spherical swarms of hundreds of thousands of stars that orbit the Milky Way in a halo, relics of the galaxy's earliest star-forming epochs. And the results have been remarkable. The globular clusters of the Milky Way, dated through white dwarf cooling and other methods, turn out to be extraordinarily old. Some of the oldest known, containing white dwarfs that have been cooling for close to 10 billion years or more. They are among the most ancient structures we can directly observe in our local cosmic neighborhood. Formed, in all likelihood, in the early universe, when the cosmos was only a few billion years old, when the first generations of stars were just beginning to process the primordial hydrogen and helium into heavier elements. These ancient clusters, and the white dwarfs within them, are windows into the early history of our galaxy. By reading the ages encoded in the temperatures of those cooling stellar remnants, astronomers can piece together a timeline, not perfectly, not without gaps, but with increasing precision, of when the Milky Way assembled itself, when its oldest stellar populations formed, how it grew and changed over the billions of years that followed. And the white dwarfs are not passive records in this work. They are active evidence. They are the physical objects whose measured temperatures, whose observed luminosities, whose positions on graphs of brightness versus color, carry the information. Every observation of a faint, cool white dwarf in an ancient cluster is an act of reading a clock that has been running, patiently and precisely, for billions of years. The white dwarfs don't know they are clocks, but they are, and the astronomers who study them have learned to read them with extraordinary care. Let me tell you about the coolest white dwarfs we have found, because here is where our journey through the deep future reconnects with the very real, very concrete, very present work of observational astronomy. We have established, at length, that no black dwarf exists yet. That the universe is too young for any white dwarf to have completed the cooling journey. That the timescales involved, 10 to the power of 15, 10 to the power of 17 years, are so far beyond the current age of the universe that not a single white dwarf has had time to finish. But some white dwarfs are further along that journey than others. The oldest white dwarfs in our galaxy, those that formed from the first generation of stars, the stars that ignited in the earliest epochs of the Milky Way's history, have been cooling for somewhere in the region of 10 to 12 billion years. They are cold, by white dwarf standards. Very cold. Their surface temperatures have dropped from the blazing 100,000-degree furnaces of their youth to something in the range of just a few thousand degrees. Cooler than the surface of our own sun, which sits at around 5,500 degrees. Cooler, in some cases, than many of the stars we see in the night sky. Some of the coldest known white dwarfs have surface temperatures below 4,000 degrees. A few approach 3,000 degrees, or even lower. These are dim, deeply reddened objects. Their light shifted so far toward the red and infrared end of the spectrum that they are essentially invisible to the naked eye, even if you were standing relatively close to them in astronomical terms. They require sensitive modern telescopes and careful analysis to detect at all. These are the oldest clocks we have, the furthest along the journey. The white dwarfs that have been cooling the longest, that have experienced the most of that extraordinary slow exhale we have been describing, that are, by any measure, the closest existing objects to what a black dwarf will one day be. And yet, even these ancient, frigid, barely glowing objects are nowhere near the end of their cooling journey. A white dwarf with a surface temperature of 3,000 degrees has an immense distance still to travel, in terms of time, if not in terms of degrees, before it approaches the background temperature of the universe. The timescales remaining for even the oldest, coldest white dwarfs we know are still trillions upon trillions of years. They are old, by human standards, ancient, by the standards of our civilization, or our species, or even our planet. But they are not done. Not even close. There is something I find genuinely moving about this. These ancient white dwarfs, these cold, dim, faintly reddened remnants of the galaxy's earliest stars, floating in the halo of the Milky Way, are the oldest things we can directly observe with our telescopes. Not the oldest light, the cosmic microwave background carries light from even earlier. But in terms of physical objects, coherent structures, things made of matter that have persisted in something close to their current form, the oldest white dwarfs are among the most ancient things in the observable universe. And they are still out there. Tonight, right now, as you listen to this, the light leaving them at this moment, faint, red, barely perceptible against the darkness of the sky, is making its way toward us, toward the telescopes that will capture it, toward the sensors and the data systems, and the patient minds of the astronomers who will measure it and think about what it means. And what it means, in part, is this. We can see the beginning of the journey toward the Black Dwarf Era. We cannot see the end. Not directly, not with any instrument we currently possess or could plausibly build. The end is too far away, the timescales too vast, the cooling too slow to observe in progress in any direct sense. But we can see the beginning. We can observe white dwarfs that are already billions of years into their cooling journey and measure how far along they are and use that information to understand not just those individual objects, but the entire history of the galaxy they inhabit. The Black Dwarf Era informs our present, not just as a future curiosity, not just as an object of philosophical or poetic contemplation, but as a scientific framework, a physical theory, that helps us understand where we came from, how old our galaxy is, what the history of star formation in the Milky Way looks like. The distant future, it turns out, is a lens through which we can see the past more clearly. There is another dimension to this that I want to spend a moment with. The study of white dwarf cooling has refined considerably in recent decades. The theory has become more precise, the observations more sensitive, the models more sophisticated. We have gone from treating white dwarfs as relatively simple, smoothly cooling objects to understanding the detailed physics of crystallization, of the latent heat released during the phase transition, of the way different chemical compositions affect the cooling rate, of the subtle influence of the crystalline structure on the thermal properties of the interior. All of the physics we have explored tonight, the neutrino cooling, the thermal radiation, the crystallization, the Debye phase, is not just speculation or extrapolation. It is tested, refined, applied theory. Theory that makes predictions about how white dwarfs of different masses and compositions should look, what temperature, what luminosity, what color, at different ages. And those predictions are compared rigorously with observations. This comparison is how science works. You build a model. You make predictions. You look at the universe and see whether what you find matches what you expected. If it does, your confidence in the model grows. If it doesn't, you revise the model, or you question the observations, or you discover something new. And in the study of white dwarf cooling, the comparison between theory and observation has been extraordinarily productive. Observations of white dwarf populations in clusters, their temperature distributions, their luminosity functions, the way the numbers of white dwarfs at different temperatures relate to each other, have confirmed many aspects of the theoretical models and refined others. The crystallization phase, for instance, the remarkable process by which the interior of a white dwarf freezes into a crystal lattice, releasing latent heat and slowing the cooling, was predicted theoretically decades before it was confirmed observationally. And it was confirmed in a beautiful piece of work using data from the Gaia Space Telescope, which measured the properties of hundreds of thousands of white dwarfs across the sky and found precisely the signature of crystallization that the theory had predicted. Theory and observation, working together. The deep future of the universe, understood through the physics of the coldest objects we can currently see. I want to linger, briefly, on the human dimension of this. Because behind all of this science, behind the theories and the equations and the telescope observations and the data analyses, are people. Men and women who have chosen to spend their professional lives thinking about the death of stars and the cooling of white dwarfs and the age of the universe. Who sit at computers in observatories and universities and research institutes, working through calculations that will never have any practical application, that will never build anything or cure anything or solve any immediate human problem, but that deepen, profoundly and permanently, our understanding of where we are and how we got here. There is something quietly heroic about that, I think. To dedicate years of your life to understanding how long it takes a dead star to cool. To find that interesting and important and worth doing. To believe that knowing the age of a star cluster matters, not because it will change anything about how we live, but because it is true, and because truth about the universe is worth knowing for its own sake. Science, at its best, is a love affair with reality, a determination to understand things as they actually are, regardless of whether the understanding serves any immediate purpose beyond itself. And the study of white dwarf cooling, these extraordinarily slow, extraordinarily cold, extraordinarily distant processes, is as pure an expression of that love as science offers. People who have never met a white dwarf, who live on a warm blue planet in the warm light of a living star, who will live for perhaps 80 or 90 years in the blink of cosmic time, sitting down to work out what happens to a dead star over 10 to the power of 17 years. And getting it right. There is, finally, something I want to say about what it means to know all of this. We are in a peculiar position, as a species. We are creatures of the Stelliferous Era, born in the warmth and light of living stars, dependent on that warmth for our existence, shaped by it in every aspect of our biology and our culture, and our sense of what the universe is and means. The sun rises and sets, and we organize our lives around it. The stars appear at night, and we have told stories about them for as long as there have been humans to tell stories. We are, in a very deep sense, children of stellar light. And yet we can think our way to the Black Dwarf Era. We can extend our understanding, through mathematics, through physics, through the careful, patient work of science, far beyond the conditions that gave rise to us. We can look at a cold, dim white dwarf in a distant globular cluster and read its age in the color of its light. We can extrapolate that cooling forward, through trillions of years we will never see, to a future we will never inhabit. We can know things that are far beyond our experience. That is, when you stop and think about it, one of the most extraordinary things about being human. Not that we live in a particular era of the universe, we have no choice about that, but that we can understand eras we do not live in. That we can reach, with our minds, into the deep future and the deep past, and find there not chaos or mystery but pattern, and law, and a story that, however vast and however strange, is comprehensible. The white dwarfs cooling in the halo of our galaxy are billions of years old. They will cool for trillions more. And we know this. We have worked it out. We have checked it against observations. We have refined it and verified it and built upon it. That knowledge, fragile, human, hard-won knowledge, carried in the minds of curious people on a small warm planet in the early universe, is one of the most remarkable things in the cosmos. More remarkable, even, than the black dwarfs themselves. So when you look up at the night sky, if you get the chance, on a clear night, away from the lights of cities, and you see the stars, know that among them, invisible to your eye, are white dwarfs. Ancient, cooling, patient objects, reading out the age of the galaxy in the fading color of their light. The oldest ones are already billions of years into a journey that will take trillions more. They are further along the road toward the Black Dwarf Era than any object we have yet discussed. And they are beautiful, even if you cannot see them. Beautiful in the way that all patient, enduring things are beautiful. In the way that anything which persists through extraordinary time, cooling quietly, changing slowly, carrying within its structure the deep history of the galaxy it inhabits, is beautiful. They are out there tonight, cooling, patient, carrying the past toward the future, one slowly surrendered degree at a time. We have come a long way tonight. Not in miles. Not in any direction that a compass could point to, or a map could chart, or a window could face. We have come a long way in time. Forward through time, further than imagination usually reaches, further than the daytime mind typically ventures, out into the cold and quiet and extraordinary depths of a future, so remote it exists, for now, only in mathematics and in the patient, curious human willingness to wonder about things that will never directly affect us. We started here, in the present, in a universe still bright with stars, still warm with the light of 100 trillion suns, still early in its story, by almost any measure that matters cosmically. A universe young enough, and energetic enough, and full enough of light and heat and activity, that darkness of the kind we have been exploring feels almost impossible to believe in, almost theoretical, almost like something that belongs to a different universe entirely rather than the future of our own. And then we walked forward, through the death of stars, through the formation of white dwarfs and the extraordinary slowness of their cooling, through the crystallization of stellar cores and the quantum mechanics of degenerate matter and the two branching futures of a proton, through the darkness of a universe without stars, through the rare, brilliant, unwitnessed supernovae of the most massive black dwarfs, through the longest timescales physics can currently describe. And now we are here, at the end, or as close to the end as tonight's journey takes us. And I want to take the time that this moment deserves, not rushing past it towards sleep, not summarizing it efficiently and moving on, but actually sitting in it for a while. Because the end of something, even something as vast and impersonal as the story of the universe's light, deserves a moment of stillness, a moment of genuine attention. Let me tell you what I find most beautiful about all of this. Not the numbers, extraordinary as they are. Not the exotic physics, remarkable as it is. Not even the images themselves, though some of them have stopped me in my tracks, metaphorically speaking, many times over the course of putting this together. What I find most beautiful is the character of the ending. Because the universe does not end violently. That is worth saying clearly, and worth sitting with, because it runs counter to a certain kind of storytelling instinct. We tend to imagine endings as dramatic, as climactic. We expect them to announce themselves, with a bang, with a flash, with some moment of recognizable conclusion that separates what came before from what comes after. The last chapter of a book should feel like a last chapter. The final scene of a film should have the quality of finality. Endings, we feel, should be legible. They should be visible. The universe, it turns out, is not interested in legible endings. The universe ends, if ends is even the right word, in the quietest, most gradual, most understated way that physics permits. Not with an explosion. Not with a collapse. Not with any single identifiable moment that you could point to and say, "There, that was it, that was the end." It ends by cooling. By the slow, patient, almost imperceptible release of warmth into an expanding space that grows ever colder, ever more dilute, ever further from the conditions that sustain the extraordinary activity of the Stelliferous Era. Star by star, the light goes out. White dwarf by white dwarf, the warmth fades. Black dwarf by black dwarf, the last traces of thermal energy are surrendered to the surrounding dark. Not dramatically, not all at once, just steadily, unhurriedly, over timescales so vast that even the concept of dramatic change becomes meaningless. The universe cools the way the last embers of a fire cool when no one is tending it, not going out in any single identifiable moment, just gradually, incrementally, barely perceptibly becoming less warm, and less warm again, until the distinction between warm and cold has ceased to be a distinction that matters. There is a word for the direction all of this is heading. Entropy. It is a word that carries a certain reputation, sometimes invoked dramatically, as though it were a force of destruction, a cosmic villain in the story of the universe. But entropy, properly understood, is neither dramatic nor villainous. It is simply a measure of disorder, of the number of possible arrangements that a system could be in, of the tendency, deep in the mathematics of statistics and probability, for systems to move toward states that are more likely rather than less likely. And the most likely state for the universe, given enough time, is one of maximum uniformity. Maximum disorder, in the technical sense. A state in which energy is distributed as evenly as possible across all the available space, with no gradients, no concentrations, no pockets of heat surrounded by cold or light surrounded by dark. Just a smooth, uniform, featureless equilibrium. This is sometimes called the heat death of the universe. A name that sounds dramatic, but describes something entirely undramatic. Not a death in the sense of violence or pain or loss, but a death in the sense of completion, of a process reaching its natural conclusion, of a story arriving, after an incomprehensible length of time, at its final resting state. The Black Dwarf Era is not the heat death. The heat death, properly speaking, lies even further ahead, after the black dwarfs have themselves faded or dissolved, after the black holes have evaporated, after whatever slow quantum processes are still occurring in the cold dark have finally run their course. The heat death is the asymptote that the universe is approaching, the limit it tends toward, the state it is always becoming, though it may never fully arrive. But the Black Dwarf Era is a significant chapter in that approach. The chapter in which the last significant concentrations of thermal energy, the cooling stellar remnants, the slowly fading black dwarfs, surrender the last of their warmth to the universe. The chapter in which light, as a meaningful and widespread feature of reality, finally and permanently ceases. After the Black Dwarf Era, there is less energy, less activity, less structure, less of anything that we might recognize as the business of a living cosmos. Not nothing, but less. Always and increasingly less. And yet, I want to resist, gently but firmly, the pull toward pure melancholy that this image can exert. Because there is something else to be said. Something that I think is true and important, and worth carrying into sleep tonight alongside everything else we have explored. The light that the universe is slowly surrendering, the warmth that the stars are radiating, and that the white dwarfs are radiating, and that the black dwarfs will radiate in their last, barely perceptible whispers. That light does not disappear. Energy is conserved. That is one of the most fundamental laws of physics, and it holds everywhere, always, without exception. Energy changes form. It transforms from one kind to another, from nuclear energy to photons, from photons to heat, from heat to the slowly expanding background radiation of a cooling cosmos. but it does not cease to exist. The light that our sun has been emitting for 4.6 billion years. Every photon that has warmed an ocean, driven a weather system, nourished a plant, fallen on a human face on a summer afternoon, all of that light is still out there, moving outward at the speed of light, in every direction, into an expanding universe. Redshifted now by the expansion of space, stretched to longer and longer wavelengths, cooling toward radio waves, and then toward the microwave background, and then toward wavelengths, so long that they carry barely any energy at all. But there, the universe, in this sense, forgets nothing. Every photon that has ever been emitted is either still traveling, or has been absorbed by something, contributing its tiny quantum of energy to the thermal state of that object, which will in turn eventually radiate it outward again. The energy moves, transforms, disperses, but persists. The warmth of every star that has ever burned is woven, in some infinitesimal and untraceable but real sense, into the fabric of the cosmos, into the background temperature of the universe, into the photons streaming through the dark. The universe carries its own history in its temperature. Think about that star we visited early in our journey. That hypothetical, ordinary medium-sized star. A star like our sun, burning steadily for 10 billion years, warming its planets, perhaps sustaining life on one of them, finally swelling into a red giant and shedding its outer layers in a beautiful planetary nebula, and leaving behind a white dwarf that would cool, over trillions of years, into a black dwarf. That star's story doesn't end with the black dwarf. The black dwarf is a chapter. A long chapter, the longest, in terms of raw time. But the energy that star spent its life radiating outward is still propagating through the universe. The planets that orbited it, those that survived, those that were swallowed, those that were flung into the interstellar dark by gravitational interactions over the billions of years that followed their atoms, were forged in earlier stars, and will go on to become something else, in some future chapter we cannot currently write. The matter that was shed in the planetary nebula, the outer layers of the star, expanding into a beautiful glowing shell before dispersing into the surrounding interstellar medium, that matter enriched the galaxy, added to the pool of heavier elements available for future generations of star formation. In a very real sense, the death of that star contributed to the birth of later stars. The carbon and oxygen in its planetary nebula became part of the raw material of subsequent solar systems, subsequent planets, subsequent life, perhaps. The story of a star is not contained within the star. It ripples outward, into the galaxy, into the composition of the next generation of stars and worlds, into the atoms of living things that will never know the name of the star they owe part of their existence to. And all of that rippling, all of that propagation of influence outward through space and time, it continues, even after the black dwarf has formed, even after it has cooled completely, even after it has, in one future or the other, either dissolved or frozen into iron. The consequences of that star's existence continue to propagate through reality, in ways that grow more diffuse and less traceable with each passing eon, but that do not simply stop. Nothing simply stops. That is the deepest thing the Black Dwarf Era teaches, I think. Not that everything ends, though in a sense everything does. But that ending and continuing are not opposites. That the conclusion of one process is always, in the economy of the universe, the continuation of another. That matter and energy, unable to be created or destroyed, only transformed, will go on being matter and energy for as long as there is a universe to contain them. Which appears to be a very long time indeed. There is a quality to darkness that we do not always acknowledge. We treat it, often, as the absence of something. The absence of light. The absence of warmth. The absence of activity. And in one sense, that is accurate. Darkness is what you have when the light has gone. Cold is what you have when the heat has faded. But darkness is also a presence, in its own right. Stand in a truly dark room sometime, or better, lie in one, in the quiet, in the early hours when the world outside has gone still. Close your eyes. Feel the darkness not as an absence, but as a texture. As something with its own quality, its own depth, its own kind of richness that the light, for all its beauty, covers over. There is something in deep darkness that is not frightening, not if you let yourself settle into it. Something that is very old, and very quiet, and very patient. The universe, in the Black Dwarf Era, is that darkness. Old beyond reckoning. Quiet beyond comparison. Patient in a way that we, with our brief and urgent lives, can barely begin to comprehend. And in that darkness, something remains. The black dwarfs drifting. The ancient crystalline remnants of stars that once burned. The gentle pull of their gravity, unchanged through all the eons of cooling. The memory, encoded in the arrangement of their atoms, of the fire that made them. Not light, but not nothing. Presence in the dark. Endurance in the cold. The universe, having done everything that a universe of stars can do, having burned and blazed and collapsed and exploded, and built complexity out of simplicity, and simplicity out of complexity, across a span of time, that makes all of human history look like the briefest spark settling, at last, into something quieter. Not finished, exactly. Not done. The quantum processes continue. The protons are counting down, perhaps, toward their eventual transformation. The picnonuclear fusion is rearranging nuclei, grain by patient grain. The black holes are evaporating, hawking photon by hawking photon, on timescales that make even the Black Dwarf Era look brief. But quieter. So much quieter. Settling into a rest so deep that the word rest barely contains it. We started tonight with a universe without stars. We imagined floating in that darkness, in that silence, with no light anywhere and no warmth and nothing but the cold, invisible presence of ancient remnants drifting through a universe that had grown too old to shine. And I said at the beginning that this was not frightening, that it was vast, almost incomprehensibly vast, but not threatening. Not hostile, just still. I hope that, having made this journey, you feel the truth of that more fully now than you did at the start. The Black Dwarf Era is not a nightmare. It is not a catastrophe. It is not the universe failing at something it was supposed to succeed at. It is simply the universe being what it is, obeying its own laws, following its own nature, moving in the only direction that everything always moves, toward greater entropy, toward greater equilibrium, toward the slow, patient, inevitable evening out of all the gradients that the Big Bang set up. It is the universe resting. After an extraordinarily long day. After having made stars and planets and galaxies and the conditions for life, and perhaps, here and there, in the warm orbits of brief and generous suns, the conditions for consciousness, for wonder, for the asking of questions about what the universe is and how it will end and whether any of it matters. After all of that, the universe rests. In the dark. In the cold. In the patient, unhurried quiet of a cosmos that has done what it came to do, and has nothing left to prove, and is content, if a universe can be said to be content, to simply be. You tonight are part of this story. Not a footnote. Not a negligible detail. A part. The atoms in your body were forged in stars that lived and died before our solar system existed. The carbon in your cells, the oxygen in your lungs, the iron in your blood, all of it made in stellar cores, scattered by stellar deaths, gathered by gravity into new generations of worlds, and eventually into you. You are, in the most literal and unmetaphorical sense, made of star stuff. And the warmth you feel right now, from whatever is around you, from the air in the room, from the blanket or the bed or the gentle temperature of a night that has settled into its quiet hours, that warmth is ultimately solar, ultimately stellar, ultimately the gift of a living sun, for 0.6 billion years old, faithfully converting hydrogen into helium in its core and radiating the energy of that conversion outward across 93 million miles of space to warm a small blue world orbiting in the darkness. You are living, right now, in the warmest and most energetic and most luminous chapter of this particular planet's history. You are here in the Stelliferous Era, the age of stars, which is already beginning its long, slow decline toward eventual darkness, but which has billions of years still ahead of it. Billions of years of stars still burning, of suns still rising and setting, of light still filling the universe in every direction. You are here for the bright part. And that is something worth knowing, quietly, in the dark, before you sleep. That you are here for the bright part. That the warmth around you right now is real and present, and the product of a universe that has been building toward it for nearly 14 billion years. That the darkness, when it comes, in its own extraordinarily unhurried time, will not be a failure or a loss, but simply the next page of a story that has always been, at its heart, a story about transformation. Nothing is wasted. Nothing is lost. Everything becomes something else, in the fullness of time, in the patient mathematics of a universe that forgets nothing and loses nothing, only transforms. And the transformations take a very long time. Long enough, certainly, to sleep through. So rest now. Let the journey settle around you like something warm, even though we have spent much of it in the cold. Let the timescales dissolve back into the abstraction they came from, and take with them any weight they might have accumulated. The Black Dwarf Era is not here yet. It will not be here for longer than the mind can hold. You are safe in the warmth of a living star, on a living world, in the bright chapter of the universe's story. The black dwarfs are waiting, patiently, impossibly far ahead. The universe is not rushing toward its quiet ending. And neither should you rush toward anything tonight. Just breathe. Let the darkness behind your eyelids be the comfortable kind, the warm kind, the kind that belongs to a living creature resting in the ordinary night of a world that still has a sun. The stars are still out there, beyond whatever ceiling is above you, still burning, still patient, still faithfully converting their hydrogen, warming their planets, shining their light across the dark. For billions of years yet. They are in no hurry. And the last of their light, when it finally, imperceptibly, extraordinarily slowly fades, will fade not into nothing, but into the deep and patient dark of a universe that has held everything, always, and will hold the quiet of the black dwarfs the same way it holds the light of the stars. Gently, without preference, without end. In the end, the universe doesn't burn out. It cools. Slowly, beautifully, into a darkness that is not empty, but full, in its own quiet way, of everything that the light once was. Good night.